As you'll see throughout this course, there are actually lots of different types of session hijacking. So I want to talk pretty generically on this slide about what we mean by the term. So let's take a user communicating to a server. The user is making requests, and of course the server is sending back responses. When we talk about session hijacking, we're talking about an attacker getting into that communication with the server, because really what the attacker wants to do is take over the victim's communication with the machine. Now that may be that they simply want to impersonate them as far as the application is concerned. Or it may mean that they actually want to boot the victim off the connection altogether, and effectively the attacker just steps in the victim's place. Depending on the style of attack, the victim could still be logged in and think that they still have a good connection, or they could actually lose connectivity altogether. And again, it really depends on the type of session hijacking attack that's being mounted. The one commonality though is that the attacker is able to step in and effectively impersonate the victim. So as far as the machine or the application that they're talking to is concerned, the session is still active, things are still progressing as per normal, but of course we've now got this attacker in here, playing the role of the victim. As I've said a few times now, there are actually different types of session hijacking. So let's go and have a look at a few of those now, just at a high level, and then we'll drill down into them in detail throughout the remainder of the course. As you'll see throughout this course, there are actually lots of different types of session hijacking. So I want to talk pretty generically on this slide about what we mean by the term. So let's take a user communicating to a server. The user is making requests, and of course the server is sending back responses. When we talk about session hijacking, we're talking about an attacker getting into that communication with the server, because really what the attacker wants to do is take over the victim's communication with the machine. Now that may be that they simply want to impersonate them as far as the application is concerned. Or it may mean that they actually want to boot the victim off the connection altogether, and effectively the attacker just steps in the victim's place. Depending on the style of attack, the victim could still be logged in and think that they still have a good connection, or they could actually lose connectivity altogether. And again, it really depends on the type of session hijacking attack that's being mounted. The one commonality though is that the attacker is able to step in and effectively impersonate the victim. So as far as the machine or the application that they're talking to is concerned, the session is still active, things are still progressing as per normal, but of course we've now got this attacker in here, playing the role of the victim. As I've said a few times now, there are actually different types of session hijacking. So let's go and have a look at a few of those now, just at a high level, and then we'll drill down into them in detail throughout the remainder of the course. When we talk about session hijacking, and particularly as I cover it in this course, it's going to get broken down into two main categories. And the first category is application level hijacking. Now, when we talk about application level hijacking, we're often talking about an application such as a web application. So effectively a web server that's serving up HTML over HTTP on the web. Now there are multiple different classes of session hijacking attack that can be mounted against a web application. So for example, session ID sniffing, where the attacker obtains the session ID that the user is using. Session fixation, where the attacker actually provides a session ID to the user, and then they pull the user's data back out based on that. Session donation, where the attacker forges a profile and gives over the entire session and the profile to the user, with the hope of the user then entering some data that the attacker can obtain. And then session ID brute force, where the attacker is actually trying to guess a valid session ID of a user simply by rapidly enumerating different possible session IDs and seeing if any of them stick. So all of these are different types of session hijacking attack that we're going to look at in terms of how they target an application. The other class of session hijacking attack we're going to look at is that which is mounted against the network level. Now we're predominantly going to be talking about session hijacking at the TCP level, which involves things like blind hijacking. So can the attacker insert themselves into the communication by guessing the sequence numbers of TCP packets? Conversely, could they just sniff that out? So could they mount a session sniffing attack, but unlike the one in the left-hand column where it's looking at the HTTP stack, do so at that TCP level in order to sniff out sequence numbers from packets? IP spoofing also features when we talk about session hijacking at the TCP level on the network. And just to round things out a little bit, it's not always TCP. We'll take a look at UDP hijacking as well. Now, all of these attacks at the network level do tend to be pretty rare today, at least compared to session hijacking at the application level, but for the sake of completeness, we are going to cover it in this course, so you're at least aware of the risk, and certainly you'll be aware of some of the history behind network level session hijacking as well. So with these types of hijacking attack now pretty broadly covered, let's move on and have a bit of a look at some of the attack vectors that we can find that allow these session hijacking techniques to take place. I want to touch briefly on 5 different attack vectors that enable a session hijacking attack to take place. We'll look at these in more detail as the course progresses, but let me just quickly cover them here to set some context as well. So one attack vector is your classic man-in-the-middle attack. So this is where an attacker can get into the communications between a victim and a target server. So for example, over a rogue Wi-Fi hotspot, or by implementing DNS spoofing, say on the router that the victim is connecting through. Man-in-the-middle attacks are a vector that lead to all sorts of different risks when we have machines communicating between each other on a network. The other one to be conscious of is a man in the browser. So now we're talking about where there might be malware or Trojans installed on a machine. Perhaps even a malicious browser add-on, so something that can execute on the host in the browser. That puts the victim at risk of session hijacking, but it also puts them at risk of a bunch of other stuff once an attacker is actually running software on the target's machine. So a man in the browser attack is pretty malicious, and session hijacking is just one of the things that can happen as a result. Another attack vector is brute forcing. So the classic style of attack where an attacker is just simply trying to force their way into a system. And in the case of session hijacking, that might mean enumerating through session IDs until they can find a valid one. That's one of the attacks that we're going to look at in more detail over the coming modules. Another classic web attack that can lead to session hijacking is cross-site scripting. And this is a topic that I cover in depth in a bunch of my other Pluralsight courses as well. So for example, my Hack Yourself First course goes into a lot of detail on cross-site scripting. Now the relevance here is that a cross-site scripting attack can then be used to mount a session hijacking attack. So one thing sort of leads to the other. And you might execute a cross-site scripting attack via a little bit of social engineering. So for example, an attacker distributing a malicious link via email and convincing the targets that they need to click on that link, which can then potentially lead into a session hijacking attack. That's another one that we're going to spend quite a bit of time on in this course. And finally, session ID leakage. So when the session ID can actually be obtained by the attacker from some other source on the web. We'll talk about the referrer in outbound links. So when a user clicks on a link, is their session ID possibly sent to another site in the referrer header? And we'll also take a look at where session IDs get exposed in log files. And that is something which unfortunately is alarmingly common. And it does lead to a potential session hijacking attack. So you can see here that we do have multiple attack vectors. And you might have initially thought of session hijacking as being a pretty simple thing, but there are a lot of different angles to it. There's a lot of different ways an attacker can actually mount this session hijacking attack. But what does it actually mean if the attack is successful? What's the impact? Let's go and take a look at that now. because it's really important to understand just how badly things can go wrong in a successful session hijacking attack. So what's the downside of session hijacking? What does it mean when the attack is successful? What's the impact? Well, there's a few different things, and clearly one of them is that the victim is now impersonated by the attacker. Now, the impact of that is really going to depend on what can a user authenticated to a system actually do. Now, that might mean everything from, say, leaving comments on a blog post through to actually transferring money between accounts. Clearly, the impact is very different between those two, and it all comes down to what is the system intended to do. What would it mean if the system actually thought the attacker was a legitimate user? Because this is the risk of session hijacking, that the attacker effectively impersonates their target. So what that means to the vulnerable system very much comes down to what that system is intended to do. So the question that you need to ask yourself is, what can a legitimate user do on a system? So let me give you an example of that. What can you do while you're logged into Facebook? What could someone logged into Facebook as you do? Look at your photos. Look at your friends' photos. Communicate with your friends as though they were you. And Facebook is a really good example because we've seen session hijacking attacks against them in the past. Let me give you a really good example of that. This is Firesheep, and Firesheep was really big news when it launched back in 2010. It was a browser plugin for Firefox, and what it meant was that an attacker could sit on a network where other people were authenticated to Facebook, sniff their tokens, and then hijack their session. And one of the big things about Firesheep was that it was just so user-friendly. If I jump down to the end of this post, we can see an image here of Firesheep running in Firefox. And in fact, what you're seeing here is 4 different people on the same network as the attacker who's running this, who are presently authenticated to Facebook. In the example here, someone has clicked on Ian Gallagher, and then on the right-hand side of the screen, we're now seeing the attacker logged in as Ian Gallagher. So Facebook actually thinks that the attacker is Ian. And now we can see part of Ian's newsfeed, and inevitably the attacker can do anything that Ian could do. The attacker can see anything that Ian could see. The attacker has effectively become Ian. This was a really serious attack, and Facebook have now well and truly mitigated this risk. And throughout this course, one of the things we're going to talk about is how this attack actually happened, and what you need to do to stop it from happening in your apps as well. So this is a great industry precedent that demonstrates just how serious a session hijacking attack can be. So now that we've established that, I want to move on, and the last thing that I want to look at in this module is just where session hijacking sits in terms of the broader spectrum of risks on the web, because it turns out that it does remain a very, very serious problem. This is the OWASP Top 10 Most Critical Web Application Security Risks. Now, OWASP is a great resource for understanding security on the web. They're the Open Web Application Security Project, a not-for-profit organisation that produces great material such as this document here. I've got many courses on Pluralsight about OWASP and their top 10. So if you want to know more about OWASP, go and check out things like my OWASP Top 10 for ASP.NET developers, or my OWASP Top 10 Big Picture course if you just want to get a good overview of what it is that they do. But what I want to look at here is session hijacking. And if we jump on down to page 6 of this document, we'll see that out of the top 10, at number 2, we have broken authentication and session management, which is very much about what we're going to look at in this course. So in their list of top 10 risks, it comes right after injection. And I've already got a course on ethical hacking, SQL injection. So if you're worried about the most serious risk, go and watch that. And then this is the second most serious risk. But why do they classify it as the second most serious risk? What is it about broken authentication and session management that has it right up here in the number 2 position? Let's jump down a few slides. And here we can see a really neat matrix that explains why it's so highly rated. And the two things here that really keep it up the top are the prevalence and the impact. So it is a very widespread risk. We do see it occur in many places. And as you see this course progress and you see how easy some of the attacks are, you'll start to realize why it is so widespread. And then of course that impact being severe. So we just looked at Firesheep, where an attacker could actually take over the authenticated session of a victim and then impersonate them when they're talking to Facebook. That is a severe impact. Put that in the context of something like banking. What if an attacker could pretend to be a legitimate user on the system and then start transferring money to other people? That is a severe impact. And that's why risks in session management are right up here in the number 2 spot. So this should erase any doubt whatsoever about just how serious this risk is and why this course is so important. If the significance of session hijacking isn't already clear, then over the coming modules, you're going to see things that will convince you how seriously this risk needs to be taken. The thing about HTTP is that it's considered stateless. So what do we mean by that? Well, it means we make a connection and then the connection gets dropped. We need something else from the web server and a new connection is made. So if we consider a user and a server, it ends up looking like this. So a request is made and then a response comes back. Pretty simple. Everything is closed off, clean slate, another request is made, and then another response comes back to the user. Same again, another request, another response. The whole thing just repeats over and over and over again. So you load up a page and you could actually be making lots and lots of connections as each asset on the page is requested. The images and the style sheets and anything else that might be embedded that the browser needs to make a new request for. The state is not maintained between each request, not at the protocol level. Let me illustrate by showing you a request. So here's what happens when I request the Pluralsight website. This is the entire request. If I come back later and make the same request, it will look identical to this. And there is nothing in here that actually says who is making the request. So have a look at what we've got. The host, the accept headers, the user agent, encoding, language. None of these things actually tell Pluralsight who I am. Yes, they could get the IP that I've made the request from, but of course you could have many people share the one IP. It's not a stable identifier of the user. So between request 1 and request 2, Pluralsight has no idea that I'm the same person. Now the caveat to that is there anything else that can be sent in the request that ties the two together? So for example, a cookie. And that's one of the mechanisms of session persistence that we're going to look at in this module. But the point here is that this is all an HTTP request normally is. And there is nothing tying them together, such as a single open connection, so that the server knows it's the same person. And that's a really, really key concept that's going to keep coming up again and again throughout this course. Now, of course, this does beg the question, how does a web app actually persist state? So for example, you can log into Pluralsight. How does it make sure that when you make the next request to Pluralsight after logging in, it still knows who you are and it doesn't just force you to log in again? You make that request and it knows who you are. It gives you access to the things you're entitled to. How does that implementation work? Let's take a look at that now. So remember that we're talking about persisting state over a stateless protocol. So that is obviously HTTP. Let's have a look at how the process of state persistence works. So we have a user and the user is going to log in to the application. So that request gets sent. The application then returns a token. Now this token is unique to the user. It's their very own one. Nobody else has the same token. Now persistence is then done by ensuring that when the user makes a subsequent request, the token is sent with it. And the server can look at the token and say, I know who you are. You're the person who just logged in. and it can then send a response which is appropriate to that user. The user makes another request, the token goes again, and then the server sends back a response which effectively is an authenticated response. So it's a response made in the context of the user's identity. It knows who the user is because the user provided a valid token. So you can see how this sort of hacks around the problem of HTTP being stateless. And the challenge then becomes how that token is persisted on the user's end. And that's what we're going to look at when we get to cookies and URLs and form fields. But before we do that, there's one other thing that I want to look at, and it's what happens on the server side. So let's think about that request lifecycle from the previous slide in terms of what's going on the server. So the server, which of course is where the application is running, receives a request that has the token. Now usually, and there are some exceptions to this that we are going to talk about throughout this course, but usually the server will then pull data about the session from a storage construct. Usually, and again there are exceptions, but usually the token will be nothing more than a unique identifier that the server can then map back to data that it is persisting. Now this leads into the discussion of, well, how does the server persist data? Well, one option is it persists it in memory. And very often, session state on the server does just exist in memory. So for example, if you build an ASP.NET application, and many other technology stacks run the same, this is a technology agnostic course, but let's say it's ASP.NET, by default it will store session state in memory. And in fact it will store it in the context of the web server process that the site is running on. If you restart the web app, or even restart the entire server, the session state disappears, it's gone. It is volatile in that regard. So this model actually ties session data very closely to the web server process. Another mechanism of session persistence is via a state server. So this would be an independent process to the web app itself, a process dedicated for just persisting state. Yet another mechanism would be to store state in the database. And these are the three options that people would normally use in a web app, such as an ASP.NET website. But again, it's technology agnostic. There are similar paradigms for other frameworks. And these actually don't matter too much in the context of session hijacking. The point is that the server issues a token and the server is able to associate that token back to data that it persists somewhere on the back end. When the request comes in with the token, the server can retrieve that data and process it in the context of the user that it belongs to. Each person's data stored in session state should be specific to them. If you give the wrong person the wrong data, that could lead to a session hijacking attack. Because in this sort of model, that session data is usually storing the identity of the user. So you want to make sure that when John makes a request to the server, John gets John's session data. You don't want him getting Mary's session data, otherwise he may well be effectively impersonating Mary. And we have the session hijacking problem. So whilst we're not going to worry too much about these different mechanisms of storage, it is really important to recognize that protecting tokens and serving the right session data to the legitimate owner of that data is absolutely critical. Now, before we move on and actually start looking at demos of session persistence, I just want to clarify one little thing first. Session ID, token, and auth cookie. These terms can be used a little bit interchangeably. They can often mean the same thing, but they do have their own semantics. So for example, later on in the course, I'm going to show how in some frameworks, the session ID is totally independent of the auth cookie. In other frameworks, they're exactly the same thing. So just take a note of these three terms and recognize that they do get used a little bit interchangeably, but that they can mean different things depending on the framework. And as we progress through the course, I'll make it really clear when I very specifically mean the unique attributes of one of these, as opposed to the generic term, which just can refer to the piece of data that the client uses to identify themselves back to the server. Okay, with that understood, let's go and take a look at how session persistence is actually implemented in web apps. What you're looking at here is my sample vulnerable site known as Supercar Showdown. I use this website across a whole bunch of my Pluralsight courses in order to demonstrate the risks that I'm talking about. So if you've seen courses such as my ethical hacking course on SQL injection or my Hack Yourself First course, you'd already be familiar with this website. Now, what you may have seen in those courses is that this is available to anyone publicly at hackyourselffirst.troyhunt.com. But what I want to point out here is that I am running this one locally. So the URL you see here says local.hackyourselffirst.troyhunt.com. This is just the version on my machine. And the reason I'm showing you this example on my local machine and not on the public website is that I've tailored the site to behave uniquely just for this example. Later on in the course we'll see the public website used, but because I need to demonstrate multiple different behaviors, I'm going to configure the site differently locally for each separate exercise. So do just take note of the URL and don't expect the behavior you see here to be behavior that you can go and experience on the live site now. Okay, with that out of the way, I want to move on and start showing you session persistence via cookies. Now to demonstrate this, I want to hit F12 to open the developer tools, and I'm going to go and drill down into the cookies. And what you'll see here is 4 different cookies. So one is called Session ID, and you can see that it's 1004751. And there's also a visit start cookie, and that's the current time in UTC. The other 2 cookies are Google Analytics. They're not relevant to this demo. Now what I want to do is go and hit the login button, and then I'm going to enter my email address and my password. Then I'll hit enter to log in, and now what we can see is up in the navigation bar it says hello Troy. So I'm now logged in. And as I navigate around the site, so say over to the leaderboard, we can still see hello Troy. We now have state persistence over the stateless protocol that is HTTP. And it's all done by virtue of this session cookie. Because effectively what the server is saying is that this particular session ID, 1004751, belongs to Troy. That's being persisted on the server side. If I was to hit delete on this cookie and then F5 to reload the page, I now see login in the navigation bar. And not only do I see login, I now see a different session ID, 1004752. So I've now got a new session ID which is not attached to an authenticated user. So you can see how this mechanism works. Login, attach the person who's just logged in to the session, and then persist the identifier of that session via a cookie so that every single request effectively allows the server to tie the browser back to the user. Now let's try one more thing. I'm going to go up and log back in, same email address, same password, and the session ID stays the same, and I am now logged in as Troy. We can see that back in the navigation bar again. Now here's what I want to do. I'm going to open a brand new tab, and I'm going to go back to the same site. And even though I'm in a new tab, I'm still logged in. We can still see hello Troy in the navigation bar. And this is the joy of cookies, in that they'll keep me logged in when I grab a new tab or a new window, or basically until that cookie expires. So if we jump back to that original tab, when we have a look at that session ID cookie, we can see that it expires in July 2016. And that's exactly 1 year from today. So I can keep closing this browser window, opening it back up, and the cookie will still be valid for the next year. It will be sent back with the request. So long as the session on the server is still valid, and that's something that we'll talk about later on in this course as well, I remain logged in. So cookies can be really handy that way. Let me just jump back to a slide for a moment, and we'll have a look at some of the pros and cons of cookie-based session persistence. Each of the 3 persistence mechanisms we're going to look at in this module have their own pros and cons. So let's start by having a look at them for cookies. So as we just saw, one of the great things about cookies is this automatic persistence. As we go to each page of the site, we're just going to a normal URL. So we're just loading up a URL, and so long as the cookie is valid for the domain and the path that we're loading, then the cookie gets automatically sent. And of course, because that session ID cookie is the one that's persisting our authenticated state, it means that we remain authenticated to each resource on the website. So that makes life pretty easy. Now, another good thing about cookies is that they're not normally logged. Now, let me explain the significance of this. What that means is that the exposure of cookies is greatly reduced as compared to, say, persisting the session via the URL. What you'll see in the next module is just how sensitive a session ID is. So by not having cookies logged in, say, your browser history or web server logs or at a proxy level, you get a whole bunch of implicit security because the session ID is that much harder to come by. And again, the significance of protecting the session ID will become very, very clear in the next module. One of the other great things about cookies is that they still work after the browser is closed. So long as they're still valid, so the one we just saw is valid for a year, when I come back to this website with the same browser, that cookie will still be sent. It doesn't get lost when I close the browser. So this means I can log on to a website, do whatever I need to do, close the browser, open it back up again, and I'm still logged in. This can be very good. So this is how I like my Facebook, for example, to run, because I want to just be able to load Facebook and I see my friends and my updates. But it can be very bad. I don't want my bank doing this. I don't want someone else to sit down at my PC and potentially see my bank account details. I really don't want them seeing my Facebook either, but they are different classes of risk. Now, one of the downsides of using cookies for session persistence is that they are at risk of cross-site scripting attacks. And we're going to have a look at exactly how that works in the next module. Now, having said that, we can secure cookies against XSS attacks, and we will talk about that towards the end of the course, but certainly they do pose a potential attack vector. And finally, one other downside of cookies is that we just saw that I opened two separate tabs, and both tabs had me logged into each one. I can't be logged into one tab as one person and then logged into another tab as another person. Now, many times this won't matter, but there are cases where it can be a downside, where you might actually want to have two simultaneously authenticated sessions under two different identities. Cookies won't let you do that, at least not in the same browser. You could always have one Chrome window and one Firefox, and each has their own cookies with their own authentication. And indeed, you could actually open up an incognito or an in private mode, depending on your browser, and effectively have an isolated instance of the same browser. But the point here is that cookies are not really designed to have multiple simultaneous sessions logged in under different users. So that's something worth keeping in mind when you're thinking about your session persistence. So that's cookies. Let's now move on and have a look at how it works when we persist a session in the URL. Let's now look at session persistence in the URL. And here's how I want to demonstrate this one. I've got a brand new tab, nothing loaded. Let's now go back to the same site. And now let's take a look at the URL. You can see there's an identifier up there that we didn't have before. And in fact, what we can see is in brackets after the host name is S, and then in another set of brackets, 1004753. And this is actually the session ID in the URL. Now, as we navigate around the site, and we again go to somewhere like the leaderboard, we can see that that part of the path stays in the URL. And then we've got /supercar/leaderboard off the tail end of that. So what's actually happening now is that we're still sending this session ID, or this token if you like, with each request, but rather than sending it in a cookie, it's in the URL. Let's open those dev tools again, and we'll go down, check out the cookies, and we'll find that there's no session ID. So we're no longer persisting via cookie. It's all being persisted in the URL. Now let's demonstrate one of the challenges with this. If I now go and grab a new tab and I go back to the same website, I now have a new session ID. So see how my session ID is now 1004754. Compare that to here, 4753. So I've actually got two different tabs with two different sessions. And it means I can actually log into each one separately because the URL is unique to the tab. It's not like the cookie that belongs to the entire browser. Now that can be good and bad. It means on the one hand that I can actually have these two different multiple simultaneously authenticated sessions, but it also poses a different challenge. Let me show you. So if I now go and log in again, same credentials as before, I'm successfully logged in, we've got Hello Troy up there, and now I go and grab a new tab and I go to the same website. Now I've got a new session ID, 1004755, and because it's a new ID, I'm not still logged in. I can go back to here, over to the leaderboard, I'm still logged in, I've still got Hello Troy up there, but because this session ID ends in 754, and this one over here ends in 755, when I go to the leaderboard, I'm not logged in. So logged in, not logged in, logged in, not logged in. You see the challenge. And certainly if I close the browser, then all of these session IDs are lost. And then I have to go and log back in again. So the longevity of a session ID persisted in the URL is not real good. Let's go and have a look at a slide on the pros and cons of persisting the session ID via the URL. So session persistence in the URL, good sides and bad sides. Well, one of the good sides is that we could have multiple simultaneous sessions in the one browser. We just saw that each tab had its own session ID, its own little isolated container of session state data, and when we logged in, its own independently authenticated tab. Now, one of the things that the URL does do quite well is it still works when people have cookies disabled. There are cases where people do not want to accept cookies. And in fact, we even see warnings legislated by the EU. When many websites are loaded, they have to tell people that they're going to be sent cookies. It almost looks a little bit scary. We're going to persist data on your machine. And some people opt out of it. The effectiveness of that messaging, and indeed opting out aside, there certainly are cases where people disable cookies. And session persistence via the URL still works when that happens. But it's not all good news for session persistence via the URL. So one problem, for example, is that as soon as you leave the website, your session ID is gone. I just touched on that when I showed you how that persistence works in the browser. So that's going to be a problem if you want long-running sessions for something like a social media site. Someone's going to have to re-log in every single time they come back, and don't just simply go back to the URL that persists the session. Another problem with session persistence in the URL is the referrer header. So when someone clicks a link and the request is made, it will attach the site that they're coming from to that request. So a user clicks a link to the external site and they're going to send the URL complete with the session ID to that external site. There are caveats when that won't happen as well, but we're going to talk about that as we progress through the course and actually demonstrate both the risks and the defenses. And finally, one of the problems with URLs is that they do tend to get stored in logs. Now that log might be cache. So if there's a caching appliance in the request pipeline somewhere, or even cached in the browser, and for that matter, cached in the browser's history as well. URLs also get logged in places like web server logs, possibly proxy logs. There are multiple points where the entire URL can be stored. And going back to the point about the session ID really being a sensitive piece of data, this does pose quite a serious risk. We're going to have a look at just how much of a risk it poses in the next module when we start actually executing session hijacking attacks. For now though, this is pretty much the ups and downs of session persistence in the URL. It certainly is quite a common thing. Perhaps not as common as cookies, but you do still see it around a lot. Let's now move on and have a look at something that we don't tend to see very much these days, and that's session persistence in hidden form fields. Now in this section, I just want to talk through a slide. I'm not going to demo persisting sessions in hidden form fields, because firstly, it's pretty self-explanatory. It's just a hidden field on a page that has the session ID. And secondly, we really don't see this happen very much anymore. So it's not particularly relevant to this day and age. But I do want to cover it here briefly in this slide. So let's talk about the ups and downs of session persistence in hidden form fields. So firstly, a little bit like the URL, you can have multiple simultaneous sessions in the one browser, because the hidden form field just exists within the page of that individual tab. It's not like they cross-pollinate from one to the other, not like a cookie does. Also, like using the URL, it will still work if the client has decided that they don't like cookies. Doesn't matter why they don't like cookies, the point is that whilst they can turn cookies off, they can't turn off the fact that a website might actually put the session ID in a hidden form field. But hidden form fields also suffer from the same problems as persisting the session ID in the URL does. So for example, it's lost as soon as you leave the website. It just existed there in the page source. Now that page is gone, the user's going to need to open up a new page and then get a new session ID. And that will probably mean having to re-authenticate again as well. One of the unique problems to persisting session in hidden form fields though, is every request now needs to be a post. You can't do a GET anymore. So you can't just have a hyperlink on a page, because that will result in an HTTP GET, which won't have a request body which can contain the session ID. There's not going to be any form data. That's what a post is for. So that's problematic, as you now need to turn every single navigation point on the website into a form post. Now what that also means is that you can't do things like authenticated embedded resources. So if you put something like an image or a video or any other asset embedded into the page, by default at least, that's going to be requested by HTTP GET. An image source, HTTP GET. Script source, a GET. A video tag, it's going to use an HTTP GET in order to retrieve the media. And because it's a GET, it's not going to send the session ID. It's no longer going to be an authenticated request. It is very rare to see this approach in a modern web application. This is very much session persistence like it's 1999. And that era is probably about right too. We just simply don't see session persistence in form fields on any sort of a regular basis. And if you do see it, it's always very odd, and it suffers from the problems that you see here. So whilst it's worthwhile being aware that such a mechanism does exist, even if it is quite rare, it's very unusual to come across a site that actually does it this way. Let's begin these demos by taking a look at hijacking cookies with cross-site scripting. And arguably, this is one of the most prominent session hijacking attacks, because as you'll see in a moment, it is exceptionally easy. So here's what we're going to do. I'm on the website, the local version of my website, and I'm presently logged in. We can see Hello Troy there up in the navigation. I'm going to hit F12 to bring up the DevTools, and we'll jump over to our resources, cookies, and then into our set of cookies. Now we can see here that I have a session ID. It's 1004756. So I'm presently logged in and the cookie is set on my machine. Now what we're going to see here is a reflected cross-site scripting attack. So let me show you the execution of the attack and then I'll talk through how it actually works. Now what normally happens with the reflected XSS attack is a malicious link is socialized by the attacker. Now it just so happens that I've got a tweet over here on another tab, and this tweet does look kind of intriguing. Troy is saying, "Oh nice, check this out. It must be something interesting." Now the link looks okay. It's to a site that I know and trust, local.hackyourselffirst.troyhunt.com. Yes, there is something off the end of this link, but all we can see is the 3 little ellipses there. So we really can't see what the actual URL is. Let's click on it and see what happens. And here we go. It looks like just a search page. In fact, the search page is saying nothing interesting to see here at all. However, the attacker has just stolen my session ID. How did this happen? Well, there's a little bit of an indicator on the screen here that I've deliberately left just to try and illustrate the mechanism. So you'll see towards the left-hand side, there's a broken image. Let's do this. I'm going to right-click on that image and I'm going to inspect the element. What we will now see is that the image source is attacker.com and then a query string of cookies equals and then session ID equals, and there's my session ID, 1004756. That is the session ID that we just saw in the other tab. Now let me first show you how the attacker can use that session ID to hijack the session, and then we'll come back and we'll look at the mechanics of how that XSS attack actually worked. So what I'm going to do is just double click on that link and I'm going to copy out the name and the value of the cookie. Let's go and put that on the clipboard. I'm now going to go and bring a Firefox session over onto this screen. And the reason I want to bring Firefox over is because I want to show you a totally separate browser, not authenticated to the site, and what we can then do with this cookie. So here's Firefox. Let's now go to the website. Now because I've gone to the site in a brand new browser, I should have a brand new session. So let's hit F12 for the developer tools. And I have the storage inspector enabled in Firefox, so we can jump over to storage. And we'll see here that we've got cookies already selected. And in fact, we can see that there is a session ID here with a value ending in 57. So remember Chrome was ending in 56. It has its own cookie ID. Now because this is a brand new session and I haven't been to the site in Firefox before, we can also see the login link in the navigation bar. So I'm presently logged out. Now let's do this. I'm going to jump over to the console, and then in the console, I'm going to write document.cookie equals, and then in quotes, I'm going to paste in the cookie that I copied from Chrome. Let's now run that. And that has now run, and we've now set a cookie to the session ID ending in 56. Let's now follow a link so that that cookie gets sent back to the website. We'll go to the leaderboard. And now we can see Hello Troy in the navigation bar. So the attacker is now logged in as me. Now what that means is that the attacker can now do whatever they like under my identity. So that's it. It really is that simple. Once the attacker has the session ID, they can impersonate the victim. And it's as simple as just recreating that cookie in their browser. Now you might be wondering, how was this actually possible? By now it should be clear what the actual session ID cookie is, but how did the attacker get it? Let's jump back to Chrome and take a look at the URL that I had posted to Twitter. So here's what happened. When we look at the search term in the address bar, we can see that the value of that search term actually has quite a bit of content in it. Now let me show you what's actually going on with this URL. I'm going to jump over into a notepad window and I'm going to paste the entire URL just here. What you're seeing here is a very basic reflected cross-site scripting attack. I'm only going to talk about it briefly here, and if you want to get into detail in cross-site scripting, go and check out my Hack Yourself First course, How to Go on the Cyber Offense. I will, however, point out the important bits here. I'm using JavaScript to declare an image, and then I'm setting the source of that image to attacker.com, passing a query string with a name, that is cookies, and a value That is document.cookie. So what's actually happening here is when this script runs in the browser, it's getting the cookie and it's appending that to the attacker.com URL, and it's setting that as the source of the image. So you can see here where the image actually gets appended to the document body. And then that's why we saw the broken image in the browser, because there is no image at attacker.com, but that doesn't matter because my cookies have still been sent off to there in a request. The last little bit of jQuery script here is just simply to make sure that that H2 heading has this little bit of text, which there's nothing interesting to see here at all. If I didn't do that, we'd actually see the search term, which looks a little bit suspicious. Now, the reason why this works is evident once you view the source code of the page. So Control U to jump into the source. I'll just jump straight down to the end, and we can see that the entire attack payload actually appears here. So that is everything that was in the URL. And really what we're looking at here is a classic reflected cross-site scripting attack. And in fact, it's this very vulnerability that I do demonstrate and explain in detail in my Hack Yourself First course. The important thing here is that this has made for a really, really easy session hijacking attack. Let's go and take a look at how this really worked by way of a basic diagram. Let's break this attack down in a nice simple visual way. So we had an attacker, and the attacker shared a malicious URL with an XSS payload. So that's what I did via Twitter. That was my tweet that had the malicious query string in it. Now the user, the victim, was already authenticated, and they followed that link with the XSS payload. Now when the application received that request, it reflected the malicious payload. So it wrote it to the page, it embedded it in the page. And of course what was embedded was a request to the attacker with the cookies. So that code loaded up in the user's browser. And of course it's the user's browser that has the session ID cookie. So that consequently caused the browser to make a request to the attacker with the session ID. And that was all it was. It was a very, very rudimentary cross-site scripting attack. But that's all it took to get the session ID. Now this is reflected XSS. It could also have been persistent XSS. So that is cross-site scripting which is actually stored in the database such that everybody sees it when they come to the site. It doesn't have to be reflected by a malicious URL. We wouldn't have had to use Twitter or email or any other channel to socialize the link because the attack is persistent in the database. So again, that's the style of attack that I go into in detail in the Hack Yourself First course. Suffice to say that once an attacker can start to run arbitrary script in the victim's browser, they then have the opportunity to hijack session cookies. Now there are defenses against this, multiple defenses, and I'll talk about those later on in the course. For now though, this is a great demonstration of just how easy session hijacking can be. In the clip you just saw, we established how easy it is to hijack a session once the attacker knows the session ID. And we used a reflected cross-site scripting attack in order for the attacker to get hold of it. But there are other risks which lead to the disclosure of the session ID from a cookie. So for example, cookies will often be captured in exception logs. There are many different frameworks out there, many different tools that aid developers by ensuring that when an unhandled exception occurs in an application, as much information as possible is logged, so that the developer can then go and review the exception and figure out what went wrong. Now, unfortunately, those logs can contain session IDs. In fact, they can contain multiple different attributes of sensitive data, but the one we're going to look at here is that session ID. Now, my vulnerable website here uses a framework called Almar, the Error Logging Modules and Handlers, and you can come across exposed Almar. And many websites that use Almar do unfortunately make the details public. So let's do this. We'll go to the LMAR exception log, which is unfortunately exposed on this application, and we can see here that there is one exception. We can see that the exception was an invalid column name, but it doesn't really matter what type of exception it was. There are many different circumstances that can lead to an exception in a web app. The important thing is that we can now drill down into this exception. And when we drill down, we get a lot of internal implementation data. Now, one of the things that gets disclosed in this internal implementation is the actual HTTP request. And of course, when you have a valid cookie for a site, the cookie gets sent in the request. So here's our session ID. Right here in plain text in the log. We didn't need to send anyone malicious links or cause requests to go to the attacker's website with the session ID. The website was already exposing it, a great big log of everybody's session ID if they had an active session on the website when an unhandled exception was raised and then logged by LMAR. Now this is a serious problem because it means that there are just all of these exposed repositories of active session IDs floating around the web. And in fact, it's very easy just to search for these. So there are Google Docs, very carefully crafted Google searches that allow you to specifically find exposed logs, not just from LMAR, but from all sorts of different frameworks as well. And there are a significant number of them out there. They're literally just a quick search away. But it's not just cookies that are captured here in this request. And in fact, if we scroll down a little bit, we can also see the path. Now there's nothing really sensitive in this path. It's just /make/1. Something then went wrong on that path, but the point is the path has been captured here. And that then leads us into the discussion about could we possibly leak sensitive data via the path? Sensitive data that could be used in a session hijacking attack. Let's go and have a look at what happens when an exception like this is raised when the session ID is persisted via the URL. So here we are on another very similar error. Same sort of exception type. Main thing is though, we can now see via the URL that the session ID is persisted in the path. Now I'm in here with my attacker hat on, and I'm looking at the exception that someone else raised. So I'm in here as the attacker who's been given a session ID ending in 758. But when I scroll down a little bit, I can see multiple points here in the exception which refer to the session ID ending in 757. So that ID has been disclosed in this exception, even though it was in the URL. So there's nothing useful in the cookies this time because we're not doing session persistence via cookies. But we can see here in the raw request, it's exposed. And we can also see down here in one of the server variables, the HTTP_ASP filter session ID, that it's also exposed. Now, depending on the framework, it'll get exposed in different places. But certainly the paradigm of an exception handling framework like LMAR logging the path that the exception was raised on is very, very familiar. But it's not just exception logs that track the path including the session ID. It happens in all sorts of other logs that are accrued just by the normal usage of the site, even when nothing has gone wrong. Let's go and take a look at the web server logs. I've got the one that this website is generating over here in Notepad. Now this is a very typical web server log format, and if we jump down to the end of this file, what you can see is a whole bunch of requests which include the entire path the request was made to. And of course, when we're persisting the session ID in the URL, that session ID then appears in the log files. Now this is a real problem because session IDs are sensitive data. We've established that by now. It's enough to allow the attacker to take over the victim's session. So storing them in plain text in a log file does pose some risks. If this log file is exposed anywhere, then the attacker can go through and recreate any of these sessions that are still active. sensitive data like this is not what you want to be logging. So there are a couple of different really basic attack vectors against session IDs persisted in the URL. Let's go on and have a look at another one that's a little bit more creative, and that's when the session ID is passed in the referrer to an external request. We've just seen how easily a session ID persisted in the URL can be leaked externally. So we saw those LMAR log files, and we also saw the IIS log files. But there's another risk with data that has persisted in the URL, and that's when an outbound request to another website sends the URL in the referrer header. Let me show you what I mean by that. I currently have the session ID you see in the URL here, the one ending in 759. Now I'm going to jump down to the bottom of this document, and you'll see down there that there's a link to troyhunt.com. Now what I want to do is show you what happens when I follow that link to this external website. And the way I want to do this is I'm going to snap the browser over to the left-hand side of the screen, and then on the right-hand side of the screen, you'll see I've got Fiddler open. Now Fiddler is an HTTP proxy tool. It's great for debugging of web applications because you can see all the requests that the web app is making totally independently of the browser. Now this is really what's going over the wire. So Fiddler is going to track the raw requests which are actually being sent to the target website. Now if you're not already familiar with Fiddler, and it is a very popular and free tool, go and check out a course like Hack Yourself First, where I use Fiddler extensively across multiple modules, and you'll get a pretty good sense then of what it can do. Now watch what happens when I click on this troyhunt.com link. We can see the request appear in Fiddler, and a bunch of other requests as well, because troyhunt.com does embed images and style sheets and all sorts of other things, and it will go on, and like most web pages, there'll be a heap of other content loaded. But let me do this. Let me just stop this capturing for a moment, and then I'll go up and click on that first request that was made. Let me now just maximize Fiddler so we get a little bit more room. And here we can see the problem. On the right-hand side of the screen, we're seeing all the request headers. So this is everything that my browser has sent to this other website, to the troyhunt.com website. And what you'll see down here under the miscellaneous heading is a referrer. So the referrer is the site that the user has come from. And of course, as we can see here, that site is the one that we were just on. And the referrer includes the entire path. So that path includes the session ID. By clicking on an external link, whilst using the URL for session persistence, my session ID has just been disclosed to this other website. It doesn't matter that it's a link to troyhunt.com, it could be a link to anything else. Following a link in this fashion will send the entire URL. And this is exactly the sort of thing that would make session hijacking a breeze, because the session ID is right there. We've just given it to this other website. Now this is just the nature of how the referrer request header works. This is what makes things like the referrer in Google Analytics work. You can go into your analytics portal and see where people have come from in order to get to your site. This is the whole point of the referrer header. But the problem, of course, is that if that previous URL contains sensitive data, that has now just been disclosed to another independent site. I don't have to show you what you can do with that session ID. We've seen that several times now. The point is, it has now been leaked. And this is what can easily lead to session hijacking by referrer header. So we just looked at how a session ID in the URL can be leaked to an external site via the request header. Now I used Fiddler for this, just simply to show what the raw request on the wire was. So the one we're looking at here is the request which would have actually landed at the target site. But the other thing that Fiddler is very good for is showing what traffic is actually going across the wire. So in this capacity, Fiddler is acting as an HTTP proxy. Now for all intents and purposes, this is just one point on the network that the traffic goes through. So it could be an actual HTTP proxy, if, for example, there is one proxy server that multiple clients route their traffic through. It could be at the router level. It could be at the ISP level. It could be any point on the network that traffic transits between client and server. So Fiddler is a great way of showing what can be seen at those points. Now we're going to talk about session sniffing. And when I say sniffing, I'm talking about actually looking at traffic that travels across the wire. So this is why we're going to use Fiddler, because it's a great example of what is actually transiting across the networks. So here's what I'm going to do. I'm going to clear everything that is currently on the screen just here, and I'm going to start monitoring again. Now let me jump back over into our sample website. Now I've set this site up again so that it's persisting sessions via cookies. We can't see the session ID in the URL anymore. And I'm just going to click one link. We'll just go to the leaderboard and we can see a request being made and of course a result loaded. Now when we made this request, we had a session ID. We can hit the developer tools and we'll be able to see that session ID down here in the cookies. So there it is. Now, as we know very well by now, protecting the session ID is absolutely critical. And one risk that we do have in web applications is an attacker sniffing data on the network layer. So effectively being a man in the middle where they can intercept or even just observe the request. So let's have a look at what Fiddler saw when we made that request. We'll jump back over there now. We're going to pause this traffic because my machine is making a whole bunch of different requests that are being captured here. Back up towards the top. We're going to select that first request that was made, and then here's everything that went in the request. Now, of course, the request includes all the cookies. So we can see the session ID in the cookie sent over an HTTP request. Now that's enormously bad news because everything that is sent over HTTP, you have to work on the assumption that it can be intercepted. And that's the case with this session ID. In fact, that's the case with what we looked at earlier with Fireship. So remember when I talked about this one? What we just saw is exactly what Fireship exploited. In fact, you can see here on the website, they talk about HTTP session hijacking. And as is made very clear here, when an attacker gets hold of a user's cookie, they can do anything the user can do on a particular website. This is a classic example of an unprotected session ID cookie. And leaking that session ID via an insecure cookie is an absolutely trivial way for an attacker to then mount a session hijacking attack. So let's go and take a look at a slide that very succinctly explains exactly what just went on with session sniffing. So here we are, very simple explanation. We have a victim who makes a request to the server passing their session ID. Now in this case, it doesn't actually matter whether that session ID is persisted via the URL or via a cookie. The point is that this is an HTTP request. It is not encrypted on the transport layer. Now we've got the attacker sitting down here, and the attacker sniffs the session ID from the victim. So how do they sniff it? It could be a rogue wireless network. So for example, a network in a public place that someone has stood up in order to entice people to connect and then siphon off their data. It could be that the victim's DNS has been hijacked and they're actually sending the request to someone else's server, to the attacker's server. It could even be that the ISP is intercepting traffic. We've certainly seen many examples of that happen in the past, particularly when there's government intervention at play as well. So the attacker sniffs this session ID and then simply makes a request themselves with the same ID. It's that simple. Session sniffing, and particularly hijacking once that ID has been sniffed, is very, very simple. Now later on in this course, we're going to talk about different ways to protect from this sort of attack. The main thing to understand now is that when that request goes over an unencrypted connection, assume that every piece of data can be observed by an attacker. All the attacks that we've seen so far in this module have relied on the attacker obtaining the victim's session ID. So the victim already has an established session, and then an attacker gets that ID by, say, an XSS attack, or being leaked in a log, or passed in a referrer header. Any one of those mechanisms, they all exploit the fact that the victim already has a valid session ID. I want to talk now about session fixation. And when we talk about session fixation, we're talking about the attacker predetermining the session ID of the victim. So what we're actually going to do here is we, as the attacker, are going to give the victim the session ID that we want them to use. And that's actually going to lead to the same end result as the previous attacks we've seen. Let me show you how it works. I'm currently in Firefox. Now Firefox is our attacker. And Firefox has a session ID that ends in 764. We can see that up there in the URL. Now session fixation can work when the session ID is persisted either via the URL or in a cookie. They're just slightly different attack vectors for both, but each does have the same end result. It's still going to be the attacker giving the victim the session ID they want them to use. So I'm not presently logged in. We can see the login link up there in the top right hand corner. So here's what I'm going to do. As the attacker, I'm going to go and copy the URL. We'll put that on the clipboard, and now I'm going to give that URL to the victim. Now how does the attacker give the victim the URL? Well, it could be via social media, like we saw at the start of this module with the XSS attack. It could be via email. It could be via any channel where you can give a URL to another person. So obviously there are a heap of different options there. So this is the assumption we're working on. The attacker can give the victim the link that already has the session ID in it. Now let's switch over to Chrome and see what happens to the victim. So the victim follows the link. We'll just paste it in for demonstration purposes. So there we go. Page is loaded. Now the important thing to realize at this point is that both the attacker and the victim actually have independent browser sessions running with the same session ID. Now this is only part of the attack. What the attacker really needs to get the victim to do is to log in. So for example, the attacker might say, hey, follow this link and then go and vote for the car that you like, or perform some sort of action which requires the victim to be authenticated. So let's now authenticate as the victim. We'll go and log in, and we'll enter the email and the password, and we'll log in. That's fine. Normal login, we can see I'm now authenticated courtesy of the Hello Troy up there in the navigation bar. But here's the thing. The victim is logged in, that's fine. But their session ID has stayed the same. And what that means is that if we now go back over to Firefox, so now we're playing the attacker again, and we reload the page, now we can see that in Firefox, it's saying Hello Troy. So what's really happened is that the attacker has actually hijacked the session, but they've done that by fixing the session ID that the victim will use. The attacker already knows what the session ID will be. So as soon as the victim themselves actually log in and their authenticated state gets attached to that session ID, the attacker now has control. So this is actually a really simple risk. And the same thing works with cookie-based session persistence if the attacker can exploit an XSS risk in the target site. So for example, they could send the victim a link which has some JavaScript in it which sets a known session ID into a cookie. Now when the victim follows that link, they'll get a cookie with a session ID of the attacker's choosing, and the same process repeats because now the victim has a session ID that the attacker knows. Victim logs in, authenticated state attaches to that existing session ID that the attacker gave them, and then the attacker does exactly this again. Just sets that session ID in their own cookie, and now they're effectively logged in as the victim. Let's go and have a look at an illustration of this on a slide, just to make sure it's really clear. So here's what we just did. As an attacker, we loaded the website. And in loading the website, it actually set a session ID. In fact, this was the session ID we got, the one that ended with 764. So the attacker now has a valid session. The attacker then gave the victim a URL with that session ID. So effectively the victim now has that session as well. The victim then went and logged in with that session ID, which of course then attached the authenticated state to their session, and then the attacker simply reloaded the page, sent that session ID back to the server, and the server came back and said, hey, this session ID is attached to the victim's identity. And that was it. It's a very, very simple attack, and it's made all the easier by the fact that we use session persistence in the URL. It is harder with a cookie because, like I said, you've then got to exploit an XSS risk as well in order to be able to actually set a cookie on the victim. So this was a very, very rudimentary attack, and there are many applications that are at risk of session fixation. Now there's a very easy test to see if an application has this risk. All you do is begin a session, see what the session ID is, and then log on. And if the session ID doesn't change, and the authenticated state is actually persisted via that session ID, there's almost certainly a risk. So do keep an eye on what happens to the session ID when a login occurs. That's the key. So that's session fixation. Let's now move on and have a look at actually brute forcing the session ID. Let's now take a look at brute forcing session IDs. And this is actually a very, very simple attack. And I want to show you just what this means. Now let's imagine that an attacker has gone to a website and they get a session ID like the one that we see in the URL just here. It doesn't matter whether it's set via the URL or via a cookie. It's just a little bit easier to demonstrate with the URL, but you'll see the relevance to both in a moment. Now what brute forcing means is that we're just going to keep trying different possible session IDs until we stumble across one that is actually attached to an authenticated user. So for example, we can look at this URL and say, hey, the session ID does look rather enumerable. It looks like it complies to a pattern that we could step through just by incrementing the values. So for example, what if we change that last digit from 6 to a 2? Well, the first thing is that the response has come back and it's now actually incremented the URL. So instead of 62, it's 67. So there probably wasn't a valid session on the server for session ID 62. Let's try 63, see if we get anything for that. It's incremented our session ID again. We're now at 68. We'll try one more. Let's try 64. And here we can now see in the navigation bar, Hello Troy. In this case, us as the attacker has simply been able to guess a valid session ID of a victim, an authenticated victim. So keeping in mind that we are here in Firefox as the attacker, and clearly we now have session ID number 64 and it's valid. Now this was possible because over here in the background, there's a Chrome session that's also authenticated. Same session ID, but it's logged in as me. So the Firefox session has been able to hijack the Chrome session simply by brute forcing, or really just guessing, a very educated guess at that because it's just simple enumeration, but it is still guessing a valid session ID. So this is just simple enumeration. Let's go and have a look at a slide just to illustrate this very clearly. So here's what happened. Very simple case of having a victim and an app, and they're talking backwards and forwards with a particular session ID. And then the attacker comes along. And the attacker is effectively just asking the server, hey, does the session ID ending in 762 exist? And a response comes back which implies that no, it doesn't. And the response that we saw in the browser just then is the server actually gave us a different session ID because the first one wasn't actually valid. So the attacker then enumerates. It goes to 763 and asks the server, and then 764, and it just keeps going until it gets a valid response. Now, of course, this is something that can be highly automated. You'd script this out, you'd run it on bulk, An attacker doesn't sit there in the browser manually incrementing the URL. Now, of course, because this is such a brute force style approach, just simply enumerating and guessing numbers, it's also the sort of thing that can be remotely detected. This would be very unusual behavior to continually see requests for invalid session IDs come in from an attacker. But detecting it is not something that applications normally do. And really there is a bigger risk at stake here that needs to be fixed. And we're going to cover the solution to this later on in the course in a subsequent module. For now though, this is the fundamentals of brute forcing a session ID. Pretty basic stuff. Let's move on and look at one final attack, and that's session donation. Let's finish the module by talking about session donation. And this isn't really hijacking per se, but it's very closely related and it's worthwhile being aware of. In fact, it involves a bit of social engineering too, which does make things a little bit more interesting. So here's what we're going to do. I'm not logged onto this website, but what I want to do now is I want to go and register. And what I'm going to do is I'm going to register an account in the name of my victim. I'll create an email address, and then I'll enter the name, and clearly my victim here is going to be John Smith. So I'll fill in his first name, his last name, and then I will enter a password. This is a password of my choosing as the attacker, and I will register. So now that I'm registered, I am now logged in as John Smith. Now remember, my victim is John Smith. And all I've done is created an account with his name. But what I'm going to do now is I'm going to take this URL that has the session ID in it, and I'm going to give that URL to John. So let's imagine John is now over here in Chrome. And by now you can probably sense what's about to happen. So John then follows this URL, loads it up, and of course John is now authenticated as John. Now, why does this actually work? Well, really what we've done as the attacker is given our victim a link that includes a session ID that has the target name already logged in against it. So when John Smith loads this page, as far as he's concerned, he is logged in because he sees his name. Now, this is really the first part of the attack, and it is a bit of social engineering. We're trying to convince John that this is him. But of course, on face value, this would be correct. This does look like him. The trick now is how can the attacker elicit more information from John? So for example, maybe the attacker would give John a link that goes to the profile page and say, hey John, your profile's out of date. You might like to fill in some additional information. Or perhaps the nature of the site that the attacker is trying to use requires John to fill out some further profile details before he can actually perform an action. So for example, like actually voting on one of these supercars. It's all about how can the attacker get John to provide information which John thinks is secure and private, but actually provide it to the attacker's profile, simply by tricking the victim into thinking that they're already logged in. Let's go and check out a diagram of this just to make it really crystal clear. So here we go. Let's start with an attacker. And the attacker registers and logs into the spoof account. Now again, the spoof account is an account that looks like one that should be owned by the victim. The attacker then gets back a session ID. So for example, they get a URL with the session ID in it. Now it could always be cookie-based session persistence, and then the attacker would need to exploit an XSS risk in the target site in order to give the correct session ID to the victim. This process would actually work either way. But again, the caveat with cookies is needing that other risk as well, the XSS risk. So the attacker gets back this session ID and then provides it to the victim. So in the example we just did with session persistence in the URL, we had that URL with the session ID that ended in 765. Now the victim is seeing this page and saying, hey, this looks like I'm logged on. It looks like I'm authenticated to this site. And based on that, the victim is happy to share information with the site because they think they're doing so privately. And one of the beauties of this attack is that it circumvents so many other controls that we put in place. So for example, even if we had HTTPS everywhere, a secure transport layer, this still works. You won't get any browser warnings like you might with, say, a cross-site scripting attack. And let's face it, people are used to going to a website and still being logged in. We have a lot of applications out there with long-running sessions because it means you can come back to the website and you're still logged in. Great for usability. So from a victim's perspective, there's nothing unusual about following a link to a website and seeing that they're still logged in. So that's session donation. Now, we didn't really hijack the session in the sense that we took a session ID the victim already had, but the end result was pretty much the same. We had the attacker and the victim both using the same session ID, and the attacker able to obtain sensitive information that the victim entered whilst logged on with the attacker's spoof account. Let's start with understanding TCP. And I want to start by actually looking at how the protocol works. And then once we've established that, we can move on and have a look at how session hijacking via TCP actually works. But in order to do that properly, we need to begin with understanding the mechanics of TCP, which is the underlying protocol that we run HTTP and HTTPS across. So let's start with how a connection is negotiated over IP. And it all begins with what's called a three-way handshake. So let's take an example with two machines, say a client and a server, but it could be any two hosts establishing a connection between each other. Now it all starts off with the first host sending a synchronized packet to the second host. You'll often see this referred to as a SYN packet, an SYN packet, which is why I've highlighted it here. And as we progress through this module, each time you see the letters SYN, that is the synchronization component of the communication. Now the second host then acknowledges this with its own SYN ACK packet, synchronize acknowledgement. And this is a response which tells the first host that the request to connect was received. Now finally, that first host then responds with its own acknowledgement, which completes the three-way handshake. So you see how both machines are communicating backwards and forwards with each other. And the important thing here to understand about TCP is this acknowledgement component of the communication. Now that's very different to UDP, which we're going to look at later on in this module. The thing about a TCP connection is that it sets up both ends with separate sockets so that they can communicate bidirectionally across a single network interface. Now this effectively results in a multiplexed communication that can simultaneously handle multiple TCP streams of data. Once this connection is no longer needed, there's another three-way communication performed to tear it down again. Now all of this is what makes TCP a reliable protocol. So that's one that explicitly acknowledges successful data transfers as opposed to UDP, which I just mentioned, which is connectionless. And it's classed as an unreliable protocol. It just sends packets and hopes they arrive at the destination. No confirmation though. Now that makes sense in cases where speed is more important than reliability, something like VoIP, for example. But apps using UDP have to work on the assumption of some packet loss, unlike TCP that has these acknowledgements. Now one of the things that makes TCP reliable is its ability to receive packets out of order and reassemble them in a logical fashion. So let's move on and take a look at how it does this using sequence numbers, because it's important to understand how those are used, because we're then going to look at how sequence numbers can be exploited when we look at session hijacking at the network level using TCP. Sequence numbers are where it all starts to get a bit interesting in terms of session hijacking at the network level. So let's take that same three-way handshake from the previous slide, and this time we'll add in the sequence numbers, which allow the TCP protocol to piece things back together in the correct order. So let's run through this again. And we start with the same synchronized request being sent by the first host, but the important thing here is that the sequence and acknowledgement numbers are both 0. Now they're not really 0. They're actually an unsigned 32-bit integer the generation of which is what makes session hijacking at the TCP level a little bit interesting. But by being an unsigned 32-bit integer, there are actually over 4 billion different possible initial sequence numbers, or ISNs as they're commonly referred to. You'll often see them represented though as relative numbers beginning at 0, because it makes it a whole lot easier to visualize. So we're seeing 0 here, but it is normally not actually 0. And I'm going to show you exactly what that packet looks like a little bit later on by opening up a session in Wireshark. We'll come back to the significance of the predictability of these sequence numbers when we come back to the actual hijacking component of this module. So, after the first host sends this request, the second host receives it and responds with the SYNAC that we saw before. Now in doing that, it's initializing its own sequence number to 0, but relaying the first host's sequence number in the ACK. So we can see here that the second host has a sequence number of 0 and an acknowledgement number of 1. Now it's 1 because it's taken the first host's sequence number, which was 0, and it's incremented it by 1. So this is effectively the second host confirming that it received, understood, and recognized the sequence number of the first host. Now finally, the first host responds by sending an ACK to the second host, acknowledging its starting sequence number and adding 1 to its own initial sequence number, which completes the three-way handshake. So far, all of this is just the negotiation. Let's now start actually transferring some data, because that's the whole point of setting up this three-way handshake to begin with. So here's what happens next. The first host now makes an HTTP GET request. It sends back the sequence and acknowledgement numbers from the end of the three-way handshake, along with the request itself, which for argument's sake is 120 bytes long. Now keep in mind that the sequence and acknowledgement numbers are in the TCP header. That 120 bytes attribute that you see here is derived by looking at the size of the packet itself. Now the second host receives this request, and because it hasn't sent any data yet, its sequence number is still 1 from the initial three-way handshake. So that was the ACK number that was sent by the first host earlier on. So it acknowledges the request from the first host by sending back the sequence number it just received in the GET request, plus the length of the request itself, thus confirming how much data was received. So that's why we see 121 in the ACK here. Now the acknowledgement itself, in this example, includes another 70 bytes of data. So you can see how each host is confirming the transmission of the other by using the sequence number and request size. And again, that 70 bytes, by the way, is the packet itself, not including the headers, which we'll take a closer look at in just a moment. Now in this particular case, the response body includes a 301 redirect. So that's now going to cause the first host to then go back to the second one and make a GET request to another resource. And in this case, it's say the login page. So the first host follows that 301, acknowledges the 70 bytes sent from the second host, and of course adds in that number 1 of the sequence number. And that's why we see 71 bytes get sent back in the ACK. So you can see how each machine keeps acknowledging and confirming the transmission of packets. So this is that whole reliable protocol thing again, where each one is checking with the other one. Did you get what I just sent you? Can you confirm it? And the resiliency is that the host can try again if it wasn't successfully confirmed. So all of this is just helping them track what's been sent and received on each end. So this is really TCP 101. The basics of communications, the three-way handshakes, the sequence, and the acknowledgement numbers. Now before we move on and actually have a look at some real packets, let's just take a quick look at everything that goes into a TCP header. So this is just to give you a bit of a sense of what goes into a TCP header. The main thing is you can see the sequence and acknowledgement numbers captured there in the middle of the screen, as well as a bunch of other data attributes that are essential to the request. So things such as the source and destination ports, for example. The rest of the content here isn't quite as relevant to session hijacking. So let's just finish this TCP overview by moving on and taking a look at a real-world example of what we've just discussed. And for that, we're going to go to Wireshark. So here we are in Wireshark. And Wireshark is really the canonical tool for analyzing packet captures. So if you're familiar with a tool like, say, the Fiddler web proxy debugging tool, think about Wireshark as being the equivalent of Fiddler, but running down at that layer 4 network level. Now I've filtered this Wireshark capture down. So you can see in the filter I'm just looking at TCP stream number 18. There's a whole bunch of packets from other protocols that went backwards and forwards over my network interface when I captured this, but I just want to focus on this particular TCP stream. Now let me start by showing you what the actual HTTP request was that resulted in the packets that you see here. So I'm just going to right click on this first item, go down to follow TCP stream, and here we can see the original GET request. It was just a GET request to www.troyhunt.com. We can see the request header there highlighted in red, the response header highlighted in blue, and then the raw response body down beneath that. So this is all it was, a GET request to my website. Let's close that and have a look at the actual packets that went backwards and forwards. The first 3 rows here are the 3-way handshake. Row number 1 we can see SYN, row number 2 is SYN-ACK, and row number 3 is ACK. And if we look at the header of those packets, we can see that this first header has a sequence number of 0. And as you can see via Wireshark here, this is a relative sequence number. So remember, this is to show things in a more human readable format. I'm going to show you the absolute sequence number in a moment as well. Now we can see the acknowledgement number is also 0, also like the diagram just before. Now if I jump down to the SYN-ACK, we can see the sequence number is 0. So remember, this is the initial sequence number of the second host responding, and the acknowledgement number is 1. So that was just incrementing the initial sequence number of the first host. You can also see those hosts in the source and destination columns as well. So the IP address is my machine, that's my internal IP address, and the destination, that google.com address, is because troyhunt.com is hosted on Google's Blogger service. So you can see the flow of data based on the source and destinations. So clearly the SYN-ACK is coming from Google back to my machine. And then eventually we've got that final acknowledgement, where the sequence number is 1 and the acknowledgement number is 1. So that's actually completed the 3-way handshake. What that means once that's completed is that my host can then send the GET request. So that's this one here. And when it sends that GET request, it's sending a TCP segment length of 660 bytes. So this is the actual contents of the request, which is what you saw in that request header just before. Now it's sending the sequence number of 1. So that was the sequence number from the earlier ACK response. And you can see here that the next sequence number will be 661, which is the sequence number plus the actual size of the packet. And of course, it's sending back the acknowledgement number of 1, which is what Google had sent me back in the earlier SYN-ACK response. Now, if we go down to where Google acknowledges that, we can see the ACK. And Google has sent back its own sequence number, and of course the acknowledgement number is the sequence number that I just sent in the row above this one. So you can see how the mechanics of this communication over TCP are all observable within Wireshark. And it all maps perfectly to the diagrams we just looked at. And this is how a TCP communication works. Now last thing, I've mentioned relative sequence numbers a few times, and obviously we're seeing relative ACK numbers here as well. Let me show you what those real or absolute numbers actually are, because they're kind of the key to session hijacking. So let's do this. I'm going to go up to Edit, Preferences, Protocols, and then all the way down to TCP. And you can see over here, it says relative sequence numbers, and it's checked. Let's now just uncheck that box, and we'll say OK. Have a look at the sequence and acknowledgement numbers now. Now we're seeing these 32-bit unsigned integers, the true values. And in fact, if we go back up to the beginning of the 3-way handshake, we can see that that initial sequence number is about 2 billion something. From there, it'll still increment at the same rate as the relative sequence numbers did, because of course that's just driven by packet size. But the point is that this is a pseudo-random number that shouldn't be predictable. Now that's where session hijacking at the network level gets a bit interesting. So let's move on and start to look at some of the ways that TCP communications can be exploited by session hijacking. I want to talk briefly about the generation and predictability of TCP sequence numbers, because you're probably starting to get a sense that this is going to play a part in TCP level session hijacking. Now the quote that you see here is from an RFC titled Defending Against Sequence Number Attacks. And this RFC was written in 1996, so this is a couple of decades ago at the time of recording. And clearly the quote here refers to an attack from about 3 decades ago. This is a very old attack vector. Exploiting sequence numbers is a very, very well-known mechanism of an attacker getting themselves into the middle of a TCP session. We know about this, and this was kind of the point I made at the introduction of this module about this being an attack from a bygone era. It's an old risk, and not one that happens a lot in the modern day. With that said, let's move on and take a quick look at the generation of TCP sequence numbers. So again, remembering that sequence numbers are somewhat pseudo-random. The ones we saw before, the relative sequence numbers, where we started with 0, was for human readability purposes. When we had a look at the absolute sequence numbers in Wireshark, we could see that they were clearly much more random than just beginning with 0. Now, one of the problems in older operating systems was the predictability of the numbers. And you'll see how a predictable sequence number can be exploited as we progress through this module. An example of predictability, though, would be something like BSD Unix. And the problem here was increasing the sequence number by a known value over a known period of time. So these are variables which could be calculated. An attacker could use this information to predict what a sequence number was going to be. Being able to do that is going to lead to the sorts of attacks we're going to look at in just a moment. I will, however, just add another point here. This was a while ago. This is a pretty well understood risk by now. And in modern operating systems, sequence number generation is deliberately designed to be non-predictable. But again, you do see TCP level session hijacking pop up in various pieces of material, and at the very least we'll treat this as a bit of a history lesson. Now there's one more thing I want to show you before we move on and start to look at the mechanics of how a TCP level session hijack actually takes place. Here are a couple of security advisories that talk about the risk of TCP sequence numbers being predictable. And it's worthwhile just taking a quick look at the genre of operating systems that this impacted. So have a look at the platforms in the browser on the left, for example. NT 3.5, NT 4. The newest one here is Windows 2000. It's a similar deal with the window on the right. And of course, if we scroll down a little bit, we can see that the publication of this particular vulnerability wasn't just a few years ago or even a decade ago. It was the last millennium. August 24, 1999. We are many, many generations of operating system further along than when predictable sequence numbers were a problem in Windows or Linux or any of the other major browser stacks out there. And I know I keep repeating this, but it's very important to recognize that predictability in TCP sequence numbers was certainly a problem at a point in time, but it is a very well-known problem that has been very comprehensively dealt with by most operating systems. Certainly the breadth of devices and embedded software we now have means that there are inevitably places left where this remains a risk. But coming back to the earlier point about how prevalent TCP level hijacking is in the broader scheme of session hijacking, it is something where the worst is well and truly behind us. But again, we are going to look at how this actually works, so let's move on and start talking about blind TCP level session hijacking. We're going to look at a number of different attack vectors for TCP hijacking, and I want to start with blind hijacking. Now, what an attacker is trying to do here is predict the sequence number that the targeted host sends so that they can create what appears to be a legitimate connection from that host. It's blind because they can't discover the existing sequence numbers themselves. They have to predict them instead. Now, this is all dependent on the attacker's ability to actually predict the sequence numbers. And it's blind in that they can't sniff the existing traffic, so they have to derive it by other means. The attacker may specifically look for at-risk hosts running versions of operating systems known to produce predictable sequence numbers. So let's walk through the process. Here's our two hosts. There's communication going backwards and forwards with sequence and acknowledgement numbers. Now let's bring our attacker in. And here the attacker is looking for these hosts at risk of predictable sequence numbers. Now once identified, the attacker wants to desynchronize the connection between machines. Basically what that means is that the attacker is aiming to change the sequence or acknowledgement numbers on the server. Now they can do this in a few different ways. For example, they could send null data to the server, which means the SYNAC numbers will increment on that end, but not on the client side. Another approach would be to send a reset flag. In fact, you may have noticed in that earlier TCP header diagram, there is an RST attribute. Now, if the attacker can send that to the server, they could destroy the session from that end. Now, once the attacker has successfully desynchronized the connection, they can then insert themselves back into the communication by taking advantage of the predictable sequence numbers and begin communicating directly with the host. Now the server is synchronized with the attacker, so they can resume the communication themselves. So blind hacking is one potential attack vector. And again, it's useful when the attacker can't actually sniff the connection, but they can exploit the predictability of sequence numbers. Let's move on and have a look at an approach the attacker can use when they can actually sniff the connection. So we just looked at blind hijacking, where the attacker is going to exploit the predictability of sequence numbers to take on a connection that already exists between a victim and a host. Let's now move on and talk about a man-in-the-middle session sniffing attack. And of course, when we talk about a man-in-the-middle, we are talking about an attacker getting into the midst of the communication between a victim and a target machine. So let's take this as an example. We've got our victim and our machine, and they're communicating backwards and forwards with all the usual sequence and acknowledgement numbers. The attacker then comes into the picture and reroutes the packets. Now, how do they do this? Well, one option would be to forge ICMP packets, so the Internet Control Message Protocol, which would give them the ability to redirect traffic between the client and the host such that it passes through the attacker's machine. Another option is ARP spoofing, so exploiting the address resolution protocol such that the ARP tables are modified via a forged ARP reply and the victim's traffic is sent via the host. Now those would both be attacks where they simply all exist on the same network. Of course, there's also physical interception of the connection on the wire as well. Either way, the attacker gets in here and modifies the existing connection to reroute through them. They are now effectively a man in the middle, and they can sniff the traffic, which includes the contents of those TCP packets. So in many ways, not that different to session hijacking right up at the application level. So that's man in the middle session sniffing. Let's move on and take a look at one more TCP level session hijacking attack, and that's IP spoofing. Here's the last TCP level session hijacking attack we're going to look at, and it's IP spoofing. Now, when we talk about IP spoofing, the attacker doesn't need to guess the sequence numbers or get in the middle of the communication because there's not necessarily a connection already open with the target machine. IP spoofing, for the purpose of network level session hijacking, takes advantage of source routed packets. So this is where the sender of a packet can partially or completely specify the route the packet takes through the network. Let's take a look at how this works. So firstly, let's bring our attacker in. Now the attacker is going to determine the IP address of a trusted host. Once they've got that, they can then construct what's referred to as a source routed packet. So that's a packet where the sender actually determines the route it's going to take. Now, of course, this is all dependent on the environment allowing source routed packets as opposed to delegating the routing to an actual router. But by doing this, the attacker is able to fool the server into believing it's communicating with the victim. So effectively, they've spoofed that address and they've just sent that packet onto the target machine. Now, once they do that, they can desynchronize that connection with the victim and resume it themselves. So that's IP spoofing. There are a number of things that have to be very specifically in place in that specific network environment for it to happen, but certainly that is one mechanism of TCP level session hijacking. That's the end of TCP. Let's now move on and take a quick look at UDP. In order to understand UDP level hijacking, let's just do a quick UDP 101. So UDP is a connectionless transmission model, and it has a bare minimum of protocol mechanisms. So for example, there's no handshaking and there's no resiliency against unreliability in the underlying network. Packets are just sent and then forgotten about. As I said earlier, this works great for communication mechanisms where speed is much more important than reliability, so again, something like VoIP, but because there's no acknowledgement of the receipt of the packets, you never know that it's actually reached the destination. Now, in some ways, that actually makes session hijacking a bit easier because we don't have hosts and clients looking for responses from the other one acknowledging receipt. What all this means in terms of session hijacking is that the attacker doesn't need to worry about desynchronizing the connection. Like in TCP hijacking, they can just send the packets and block packets without having to worry about anything like acknowledgements. So let's take this as an example. The victim sends a UDP request to the server. We're going to bring our attacker in, and before the server has a chance to respond with its own UDP packet, the attacker is going to forge a response to the victim. So this is a bit of a race condition. So long as the attacker can get in first, they will be the one who successfully sends the response. But the attacker could go even further if they can successfully mount a man-in-the-middle connection, because they could look for that response from the server and simply block it. The server isn't expecting an acknowledgement from the response. This isn't TCP anymore. So it really has no way of knowing that its packets have actually arrived at the victim. So there are a couple of different levels there for the attacker. And clearly forging its own response and beating the server is a very time-critical exercise, whereas blocking the response does require a man-in-the-middle attack as well. So that's a couple of different ways of hijacking UDP. Let's now move on and take a look at something a little bit different, and that's a man-in-the-browser attack. The last attack I want to look at is a man-in-the-browser attack. So let's assume we've got our victim and we've got our host. Now we'll bring in the attacker. And the key thing here about a man-in-the-browser attack is that the attacker is going to infect the victim's browser with a Trojan. Now, I don't want to trivialize this. This is not necessarily a simple thing, and we are working on the assumption that the victim has some sort of vulnerability in their browser or their operating system that allows the attacker to do this. And you'll often see this as just one line item. Attacker infects victim's browser with a Trojan, as though it's a simple thing. But there's a huge amount of effort and defense that goes into protecting browsers and operating systems from this style of attack. Having said that, it does happen. So for example, we see exploits against plugins like Flash and Java, which can lead to drive-by attacks. The victim just visits a site and an exploit in a vulnerable version of a plugin executes code on their machine. Conversely, when we're just talking about browsers, we've seen browser plugins or extensions which have been malicious in the past. And the key thing here about a man in the browser attack is we're saying that there is malicious software that's running in the browser. Now what that means is that when the victim browses a target site, the Trojan can execute and extract data from the DOM. So what would be useful within the DOM of a browser? Well, clearly anything that is actually entered into the browser. Credentials, for example. Anything that persists in the browser. Cookies. We've looked at session cookies extensively already in this course. Naturally, there are also URLs that malicious software executing in the context of the browser could have access to. And the point with all of these is that the malicious software on that victim's machine is pulling data from the DOM and inevitably sending it back to a point that the attacker has access to. A command and control server, for example. So this attack is really quite different to all the ones we've looked at already. It's not exploiting a risk in the web application itself, and it's not exploiting any sort of risk at the network level either. It actually has to compromise the host. So that's a man in the browser attack. And session hijacking is just one of the nasty things that it can do as a result of that. Let's now go and round out the module by taking a quick look at a really good example of session hijacking in the wild. I want to round out this module by leaving you with this example of session hijacking. And it really is a canonical example. In fact, it's frequently the example that is pulled out in order to show just how much damage can be done with session hijacking. I'm not going to go through it all in detail, but there are a few key things here. So number one, Kevin Mitnick, a very big name in the security scene. He was particularly prevalent for nefarious activity back in the 90s. And that's the second point I want to make here. This attack is from 1994. It's more than 2 decades ago. So again, there's this observation here about the age of TCP level attacks and the issue of how relevant they actually remain today. But number 3, this was actually a serious attack. He did manage to hijack that session, and that did form part of what was a rather large amount of havoc that Mitnick caused back in the 90s. So this is far from a hypothetical risk, or at least it certainly was back in the 90s and the early noughties. And even though the relevance is more questionable today, this is still a valid history lesson. It's always useful to understand how the technology landscape has evolved. So don't discount this entirely, but it's also not something that you need to worry about quite as much today. I want to start here because this is one that probably was fairly apparent to you as I went through the module on session hijacking in web applications. And it all has to do with the strength of the session IDs. So here's what I mean by that. This is clearly bad. Just have a look at it. It's innumerable. And in fact, back in that module, when we looked at things like brute forcing the session IDs, it all came down to how predictable that session ID was. If it is something that an attacker can guess within a reasonable amount of time, then you've got a serious problem. And obviously the issue with the ones that you see here is that they're sequential. They're just incrementing by 1. And it doesn't take an attacker very long to figure that out. They can just create a few brand new sessions and see what ID they get. Is there a pattern here that they can then replicate? Now let's compare those ones to these ones. These are all session IDs generated by Microsoft's ASP.NET framework. This is what comes out of the box. If you put something in session state in ASP.NET, you're going to get a session ID that looks like one of these guys. And clearly, these have a much higher degree of randomness than the ones on the left. In fact, let me show you just how random they are. This is a pretty solid degree of randomness. And inevitably it is pseudo-randomness, but certainly for all practical intents and purposes, an attacker isn't going to be just working through and brute forcing these IDs. They're not going to look at a sequence of generated session IDs from the Session ID Manager class and then be able to derive other valid session IDs. It's just not going to happen. certainly not in any real-world practical way, short of any yet-to-be-disclosed zero-day vulnerabilities that might compromise this. So this is great, and what I really like about the way ASP.NET manages its session IDs is that the framework does it for you. And to that point, it's not just a .NET thing. Many frameworks will produce pseudo-random IDs that are going to be resilient to the sort of attacks that relied on predictability that we looked at earlier on in this course. So the lesson here is actually really easy. Delegate to the framework. Don't roll your own. Don't try and create your own session IDs, particularly not when they look like the bad examples from the previous slide. So it's a bit of a win-win. You get the framework to do the work, and you get a stronger session ID. But of course, here's the one constant across all of this. They shouldn't be enumerable or predictable. It is that simple. That is absolutely Session ID Generation 101. It is the most important possible starting place for understanding how to protect session IDs. But it is just a starting place. Let me get this one out of the way really early, and I suspect it would have been pretty clear in the earlier module when we looked at hijacking sessions in web apps. And it's simply this: keep those session IDs out of the URL. You really do not want to be persisting your sessions that way. There's just too many problems. People will copy and paste those URLs. I have done it myself. I've tweeted a link that I thought my followers would find interesting, and then I had all these people reply to me and say, hey, your personal details are on that page. I had no idea. It is just too easy to do. Those URLs will get passed in the referrer header as well. Shortly, we will look at a way to make this more secure, but certainly this remains a serious risk. You really don't want an app to be leaking the session IDs of its users to external websites. That's a terrible security position to be in. And of course, URLs do get logged all over the place as well. And when you've got the session ID in the URL, that piece of sensitive data is going to end up in plain text in all sorts of different places. Now, yes, this will mean that if someone has cookies disabled in their browser, they're not going to be able to log on. So there is a business decision that has to be made here. Do you want those people using your site or not? But there's lots of devil in that detail. How many people? How important is it to authenticate? And then can you put a cost around the risk of if you do persist session IDs in the URL and it's exposed by any of the flaws that we've talked about throughout this course? So I am pragmatic enough to say make a value-based decision according to the nature of your site, but certainly this is not a desirable position, and your default stance should be only persisting via cookies. Many frameworks, like ASP.NET, can be configured to detect if there's support for cookies or not, and then fall back to the URL if there's not support. So that's a good middle ground, but I'd still be very worried about those people who don't have cookies and are now persisting those session IDs in a pretty insecure manner. So unless it's absolutely critical, it's cookies all the way, nothing in the URL. Let's now move on and start to look at what happens to a session ID when someone actually authenticates to the system. One of the problems we saw earlier on in the course was session fixation, and this is a serious risk in terms of session hijacking. You see this very often within systems, and of course the problem there is that the attacker predetermined the session ID that the user was going to use. So the attacker knew what the session ID was. The victim then logged on and had their authenticated state attached to that session ID, the one the attacker already knows. So this was really all about session fixation exploiting those reused session IDs. That is, the session ID that was still used once the user was authenticated. Now the fix can be very simple. Just transfer the session to a new ID once they've logged on. If the original session ID is invalidated after the user authenticates, then the risk of session fixation goes away. because the ID that the attacker has is now no longer valid. In fact, there's a really easy test to see if an application might be at risk of session fixation. You go to an app, you see what your session ID is, you log on. If the session ID is still the same, there's a very high likelihood that there's going to be a session fixation risk. So that's a pretty easy thing that you can test in any app, because of course it's very easy to look at the session ID you've been given. But there is one other approach I want to talk about, and that's not actually attaching the authenticated state to the session at all. Now that might sound a bit odd, but that's what ASP.NET does by default. And in order to show you what that looks like, I'm going to jump over to the live public version of the vulnerable website that we've been using throughout this course. So here we are back on the site, and do just take note of the URL. So this is the one that's at hackyourselffirst.troyhunt.com. You can go there right now. This is the live website, and you can go and see exactly how this behavior I'm about to show you is implemented. Now, as you can see, I'm not presently logged in. I've got the login link up there in the navigation bar. What I want to do now is just open up the dev tools. So F12 to pop them up. Now let's go and look at the cookies. And here's the main thing I want to point out. We can see that there is an ASP.NET_session ID. And this is the default cookie name for the way ASP.NET persists the session. Now note the value of this. And this has been generated in exactly the fashion I just showed in the earlier slide that explains how ASP.NET creates its session IDs. So clearly this is actually a pretty strong ID. But just note how this session ID ends with the characters 3B. Now I'm going to go and log in. I'm going to enter my email address and my password. Now have a look at our cookies. We've still got that ASP.NET session ID cookie, and it still ends in 3B. But there's now an auth cookie beneath that. And in fact, you can see the auth cookie is actually quite a bit longer. Now here's the crux of what I wanted to show you. ASP.NET separates the persistence of data in session state with the persistence of authenticated state. So that auth cookie is totally independent to the session ID cookie. Just because we're now logged in, nothing is actually changed in session state on the server, not for that session ID. So this cookie actually contains a forms ticket, which is encrypted and signed and tells ASP.NET who I am. Each time I go back to the site, the cookie is sent back to the server, ASP.NET decrypts it, and then knows who I am. Now, this is actually important for a few different reasons. One of them is that the session fixation risk has gone away. Nothing has been attached to the actual session ID cookie, and if the attacker tried to mount a session fixation attack by setting the auth cookie, once I logged in, I'd actually get a new one because again, this cookie contains a forms ticket which is unique to my identity. I'd get a different value when I actually authenticated. The other thing that's important about this is that there's not really any session-based server-side persistence of the authenticated state. Now, what I mean by that is that there's nothing sitting there in process or in a state machine or in a database or any of those other session persistence mechanisms we looked at earlier on in the course that map back to this auth cookie. The auth cookie is entirely self-contained. Every time it goes back to the server knows who I am. Now that means that the server also can't kill my authenticated session because I don't have an authenticated session. I just have this cookie that explains who I am. Now the final point I'll make here is that this does actually pose a bit of a risk insofar as if you do put something sensitive in session state, so for example, something specific to the user after they've logged in, the session fixation risk remains. So the attacker could predetermine the session ID for the user logs in and gets this auth cookie, the session ID does not change, and then the app actually starts to put some personal information into session state, and the attacker makes a request with that predetermined session ID and gets the data back out. Now ideally, ASP.NET should be rekeying this session ID So you should actually get a new ID after you authenticate. And there are libraries out there to help you do that. But I don't want to get too bogged down in ASP.NET. I wanted to talk more about the behaviors and show you some of the pros and cons of the way it's implemented in a framework such as Microsoft's. That's enough now for how we generate and issue session IDs. Let's move on and start to have a look at one of the really important attributes of cookies that contain session IDs, and that's the HTTP only flag. Earlier on in the course, I showed how an attacker could use a reflected XSS attack to gain access to the session ID cookie and exfiltrate it off into their own environment. And in fact, what we did was we set it as the source of an image that was passed as a malicious payload by the attacker to the search page. Could have also worked via a persistent XSS attack stored in the database. And the real issue here comes down to the fact that the client could access the session ID cookie, so the browser could. Now the thing is, session IDs are really there as a server-side construct. It's for the server to persist sessions, and there's absolutely no reason that the client actually needs to access it. So the browser shouldn't be allowed to run JavaScript and access that session ID cookie. There's absolutely nothing the browser needs to do with it client-side. And there's a really simple fix, which is just to flag the cookie as HTTP only. Because once it's an HTTP only cookie, then JavaScript can no longer get access to it. I want to show you exactly how that works. So let's jump back into the browser and have a look at my modified app that now treats this session ID just a little bit more securely. So I've loaded up the version of this vulnerable website that is running on my local machine. So just take note of the local prefix there in the URL. This isn't the one that you can go and use on the external web now. Now the first thing I want to do here is open up the developer tools and have a look at our cookies. So F12 will fire those up into the cookies. Let's take a look at what's been set, and we can still see our session ID cookie here. It's still using a bad session ID value, which we know we shouldn't do anymore, but that's not really what we want to look at here. The important thing is, take a note now of that HTTP column. It has a tick in it, which means that this is now an HTTP only cookie. The other three cookies are not: the visit start and the 2 Google Analytics cookies. Let's have a look at what that now means when there's an XSS attack. I'm going to close the developer tools and I'm going to paste in the URL. That's the reflected XSS attack. So this is the one that we'd followed from Twitter in the module on hijacking sessions in web apps. So let's paste it in and load the page. And this still looks very similar to the attack that we saw earlier on. We've got that broken image off there to the left of the screen. Now, if you recall, in the previous attack, the source of the image actually sent all the cookies with it. Let's go and take a look at that now. I'm just going to jump over there, right-click on the image, and jump down to Inspect Element. Now, when we do this, we can see the source of the image here, and we can see this cookies query string being passed again. We can see the visit start cookie and the 2 Google Analytics cookies, but we can't see session ID. So the browser has gotten access to every single cookie that isn't flagged as HTTP only, but it can't do anything with the one that is. So just by simply flagging that cookie as HTTP only, we have put a serious stop to the XSS attack that gained access to it before. Every cookie, by default, should be HTTP only unless you explicitly need to reference it via client script. And that's normally a very small percentage of them these days as well. So that's the HTTP only flag. Really simple to do. Absolutely positively make sure session cookies are flagged with that, and it is enormously effective against stopping XSS attacks, which then lead to session hijacking. I now want to take a look at transport layer security. And there are actually a number of advantages you get from serving web content over HTTPS. Now, first and foremost, we should be considering session IDs to be sensitive. And sensitive data requires transport layer security. A lot of people get this right for things like credentials. So when you log on, they'll post to HTTPS because of course usernames and passwords do need to be protected, but then they'll neglect the session ID. And that's exactly the risk that Firesheep exposed. So that was the Firefox plugin that I showed you earlier on in the course that allowed an attacker to simply take over someone's session. Once that traffic goes over HTTPS, that risk goes away. The sequence number prediction risk that we saw in the previous module around network level session hijacking as well, that risk goes away because you're getting encryption all the way from the client to the server. Anything sitting in the middle simply can't do anything with the traffic. They can't read it, they can't change it, and they can't redirect it. Transport layer security does mitigate against a whole bunch of different session hijacking risks. So man in the middle being one of them. And I spoke earlier on about how it could be someone who owns a malicious wireless hotspot, could be an ISP, could be government intervention. Encrypting the traffic using HTTPS puts a stop to all of that. And of course, amongst all of that, it puts a stop to someone sniffing the cookie. It also stops things like DNS poisoning. So what if the attacker could actually change the resolution of host names to IP addresses such that your traffic went somewhere else? Without a valid certificate from the server, which of course is exactly what transport layer security does, the connection gets dropped. But there's also this last point, and I demonstrated that earlier on in the course as well. Having the referrer header sent to external sites. In fact, I showed how problematic that could be when session state was persisted via the URL, because effectively you're sending the session ID to arbitrary external third parties. Let's now go and have a look at how that changes when content is loaded over HTTPS. So I've gone back to the live website, and I'm using this one because I do have a valid SSL certificate on this site, and I can demonstrate a before and after state. So just as a quick refresher, this page is loaded insecurely. This is an HTTP connection. I'm going to turn on the DevTools, and then I'm going to jump down to the bottom of the page. Now we're on the Network tab. Let me follow this link to my blog. And then I'm going to scroll back up to the top of all of these requests, look at that first one, and in the request headers over here, we can see the referrer being the Hack Yourself First website. Now this referrer includes anything in the path as well. We saw that earlier on in the course when I showed you how the session ID in the URL could be sent externally. Let's now play this whole thing out again. I'm going to go back to the previous site, and I'm going to change the scheme to use HTTPS. So it's going to be a secure connection. Let's do the same thing again. We'll jump to the end of the page. Now let's go and hit the link to my blog again. Also the same thing again. Scroll up to the top. Let's look at the first request here, and then go down and find that referrer header. It's not there. In fact, if I make this a little bit larger, just to check, there are all the request headers. There is no longer a referrer because we have come from a page that was loaded over HTTPS. So see how HTTPS not only secures the site you're on, but it also then keeps information away from the sites that you then follow links to. So using transport layer security actually gives you multiple benefits. It's not just about keeping things away from a man in the middle. It's about keeping things away from people on totally unrelated websites. And that is a really, really beneficial advantage of using HTTPS. But we can make this better again. Let's move on and have a quick look at secure cookies. I now want to take a quick look at the secure attribute on cookies. And what we're talking about here is flagging a cookie such that it can never be sent over an insecure connection. And that is exactly what should happen to the session ID cookie. It should never go out in the clear. It's sensitive. We want to protect it. And it's very easy to flag it so that this just simply can't occur, even inadvertently. Let's jump over to the publicly facing version of the website we've been using, and I'll show you exactly how that works. So here we are back on the website, and as you can see from the nav bar, I am logged in. If I hit F12 to jump into the DevTools, we can then go over to our cookies, expand that out, and we'll see that we've got that auth cookie, which I referred to just a little bit earlier on in this module. Now that auth cookie is not flagged as secure. In fact, that whole secure column is empty. None of these cookies are secure. And what that means is that all of them will be passed over an HTTP connection. So let me show you what the risk of that is. If I go up here and change the scheme to HTTPS, and then I load this, this is an HTTPS connection, but we're now going to go and have a look at our network tab. Now here's the thing, the request for hackyourselffirst.troyhunt.com went securely, but let's go and take a look at one of these PNGs down here. Now notice how the request URL is actually an HTTP URL. So this image has been embedded on the page insecurely. And in fact, that's why we've got the gold triangle on the padlock up there. Now this page is suffering from what's known as mixed mode. It's an HTTPS page, but then it's got insecure content on it. Now this is something I talk about in a lot more detail in my Hack Yourself First course. But let me quickly show you what the problem is here. I'm going to scroll down a little bit so that we can look at the request headers. And you'll see here that in the request headers, so again, remember this is an insecure request. A man in the middle can observe this one. But in this request header, we've got the cookies, and you can see there the session ID and the auth cookie that I showed you just before. Remember, that's the one that ASP.NET persists separately to the session ID when you log in. This is really sensitive information. This is session hijacking if an attacker gets hold of that cookie. Now what I want to do is show you what happens when there's a secure cookie. And here's how I'm going to do this. I'm going to jump on over to the console, and you can see a bunch of warnings there about mixed content. And I'm going to set my own cookie. And here's what I'm going to do. Document.cookie equals, and we'll just call it my name, and we'll give it a value of my value. But then I'm going to add this secure attribute. Secure equals true. Let's set that. So we've now set that cookie into the browser for the domain that we're currently on. And in fact, we can now jump over to resources, and you can see the cookie there, and you can see that tick in the secure column. So have a look at what this means. I'm going to go up and reload the page, and then I'm going to jump to the network tab while that's happening. And let's now have a look at both the secure and the insecure requests. We'll go up to the top and check the first one. So we can see that the request URL is indeed an HTTPS address. Let's now go down to the request headers, and we can see that right at the end of the cookies there, my name equals my value. So this cookie was sent. It was a secure request, so that's just fine. Now let's go and check one of these PNGs. So remember the PNGs were embedded insecurely. We'll go and open up number 2. We can see the request URL is using the insecure scheme. Let's go down to the request headers. And now here's the thing. There's no my name equals my value. That cookie that is flagged secure hasn't been sent. Now that's what should be happening with any sensitive cookies, like this auth cookie. Now of course, the images really should be loaded securely as well, because we don't want to have this mixed mode problem that we've got at the moment. Now of course, what should really be happening is that the images should be loaded securely, because we really don't want to have this mixed content problem that we've got at the moment. But flagging the cookie as secure ensures us. It makes sure that if ever there is a bit of a mistake, and say a protocol relative URL isn't used, and instead a developer explicitly puts in HTTP as the source, by flagging the cookie as secure, it simply will not be sent over an untrusted connection. So that's another really simple thing to add into any cookie that carries sensitive data. And just like the HTTP only cookie, I strongly recommend making that the default position. Make it secure by default. And then if ever there's a case where you need to send it in securely, then just change it at that point. It's as easy as that. One aspect of session hijacking we haven't really touched on is the expiration of session cookies, and indeed sessions themselves. And what I'm going to talk about here is a bit of a case of finding the right balance. This is not about making it secure versus insecure. This is about minimizing the window of risk, but it does also have a bit of an impact on usability. Let me explain. You can only hijack a session whilst there's a valid session to be hijacked. Now that may sound pretty self-explanatory, but just think about it for a moment. If we could expire the session, and then the attacker got hold of the session ID, they couldn't do anything with it. Likewise, if we could expire the cookie early, such that the user no longer had it, then that would minimize the risk. And it's worthwhile just quickly clarifying the difference between these two things as well. An expiry on a cookie tells the browser how long to keep it for. After the expiration, the browser discards it won't use it anymore. An expiry on the actual session running on the server tells the server when to purge that data that it has sitting there in process in memory, or in a state machine, or in the database. But there's a point at which the server will discard the data. So just remember, there are these two related but different things. Let me give you an example of what I mean by that. I'm going to jump back over to my local version of the app. It's presently persisting the session ID via a cookie, so we can jump on into the DevTools, over to the cookies, into the list of them, and we can see our session ID in there, 1004771. We're still using those terrible predictable session IDs right now. Now, one of the things you'll notice here is the expiry, and it's expiring in July 2016. So that's a year from the point of recording. So one of the really important things I want to point out here is this necessary? Does this need to run for a year? Because at the moment, for the next 12 months, every time I make a request to this site, the cookie's going to be sent around. If someone hits me with an XSS attack, they're going to get it. Even if someone sits down at my PC, this cookie's still going to be there and still valid. So one of the things you want to think about is what is the right expiration for the cookie. So for example, should it just be a session cookie such that when the browser closes, it disappears? But of course, some people do leave their browsers open for a very long time. Should it actually be a 20-minute expiration? So say a banking application. Banks expire sessions very, very quickly. On the other hand, if it's a social media application, you may have a very long expiration because people want to be able to stay logged in to the site. So there is a discussion there. There's pragmatism required. But here's the other thing I want to point out. So this cookie expires in a year. I want to go and restart my local web server and show you what happens to this session. I'm going to switch over to a command prompt and I'm going to just restart IIS. Now what's going to happen when I do this is the in-process session is going to be discarded. So the data that this web server was persisting that belongs to that session ID is going to disappear. Let's now flick back to the website and reload it. Now here's what's going to happen. The web server is going to get this session ID sent to it. So 1004771. And the web server is not going to have a session to actually match that to because we've just discarded it on the server side. And as we can see now, it's actually responded and given us a different session ID. It said, hey, I don't have one, here, have a new one. And this is the point that I was trying to make between the duration of session persistence on the server and the duration of persistence of the cookie on the client. Now, in some ways, this is actually good because it means that we can expire the session on the server. And when you're persisting the authenticated state by the session, it also means that you can log people out centrally. You can't do that with the ASP.NET implementation of the auth cookie that we looked at a little bit earlier on. And in fact, this is one of the things I talk about at length in my Secure Account Management Practices course. There are pros and cons to each approach. The important thing is actually understanding which one the application you're looking at uses. So that demonstrates the mechanics of how that session ID expires and also how it relates to the actual session state on the server. Let's just jump back over to the slides for one more point. Don't rehydrate an expired session with the same ID. This puts the app back at risk of session fixation, because the attacker can take any ID they like, one they may have used that has since expired on the server, and just give it to the client. The behavior that we saw just before is actually the right way of doing it, where we passed a session ID to the server that was for a session that had expired. We restarted IIS so the session state was discarded because it was managed in process, and IIS came back and actually gave us a new session ID. It was a bad session ID, it was just an enumerable value, but it did give us a new ID. And ideally what should happen is the app will hand out a new strong ID, something not enumerable. But the point remains the same. Once a session ID has been finished with, it should never be used again, even if the client gives it back to the server. We're talking a lot about session expiration in this module, and I want to run you through how the server actually handles session expiration on its side. Now let's take a fairly typical case, and we say that the server keeps the session alive for 20 minutes. So the user comes to the site and the server sets a timeout to keep the session alive for the next 20 minutes. But then the user comes back and makes another request. So the server extends the session so that it's still 20 minutes before it expires. And then the user comes back again and the same thing happens again. So this is called a sliding expiration, where that expiration time keeps sliding in response to the user still being active on the site. So really the way of looking at this is the server is saying, hey, I'm not going to throw away the session until the user hasn't done anything for 20 minutes. So that's enough time to assume that they've finished with the session. It can now be discarded. Now that's normally configurable. It's always the same duration from the last point of activity. Now the problem with this is that there's always going to be 20 minutes where that session is still valid and is at risk of a session hijacking attack. Now the attacker still needs to get the session ID somehow. It needs to be leaked or obtained by an XSS attack or something like that, but it will still be valid for 20 minutes. Let's go and compare that to having an absolute session expiry. So here's the difference with an absolute expiry. Let's start the same way. User comes along, they've now got 20 minutes before it expires. 5 minutes go by and they make another request. Now there's only 15 minutes until expiry. So see how it's still the same expiry date as it was after the first request. Another 7 minutes go by and they make another request. So now they've only got 8 minutes left before their session expires. So this is the fundamental difference between a sliding expiration, where there's always going to be this set window of risk for session hijacking, versus an absolute expiry, where the window of risk is a lot smaller. But of course there is also usability risk here. Once you start getting down to a small number of minutes, let's say we get down to 3 minutes, the user goes and gets a coffee, comes back to their desk, and they're logged out. So this is that trade-off that I've mentioned a couple of times now. Do you make it more secure or do you make it more usable? What is the right balance? There is no one-size-fits-all answer here. It's all about understanding the trade-offs. What's the benefit? What's the downside? What should the application you're looking at choose in order to strike the right balance? But there's one other thing we can do to both make this more secure and not impact usability too much. Let's go and take a look at that now. So this one is actually pretty fundamental, and it's simply this. A session can't be hijacked if it is no longer valid. If you can encourage users to log out once they're actually finished with their session on the site, then that goes a long way to mitigating the risk. I've just picked a few sites here that are probably familiar to you. Twitter, Facebook, and LinkedIn. Easily accessible logout links on every single one of these. And if I was to go and follow any one of these, and then someone had my session ID from somewhere, or indeed even if they sat down at my PC, they can now no longer compromise that site. So this puts a dead stop to session hijacking once the session is actually gone. Now, of course, the nature of all these three sites here is that people do like to have long-running sessions, myself included. I like being able to come back to Facebook without having to log on every time. But it's really critical to provide this functionality, and depending on the nature of the app, even encourage its use, because it's far preferable that the user decides when their session ends than that it's left open when they don't actually need it. So just closing the browser won't necessarily be enough. Now, of course, that does actually raise another question as well, and it's this. This goes to what I've mentioned a few times now about the cookie being somewhat independent to the session state maintained on the server side. If someone's logging out, you do want to make sure that it's not just a question of the cookie on their machine being expired, and that the session on the server side does actually expire as well. It's an easy test too. You just save the session ID from the client, log out, and then recreate that cookie back on the client. Can you then go back to the website, make a request, and appear as though you're authenticated? So that's the test, making sure that it is actually ended on the server as well. Because otherwise, if an attacker did obtain that session ID at some point, they'd still be able to actively use it, even though as far as the user is concerned, they had logged out. So there is a little twist there that you need to make sure of as well. Now there's one more thing I want to look at before we wrap up this module, and that's re-authenticating before key actions. This one is a good mitigating control for the risk of session hijacking. So let's assume for a moment that someone's session has been hijacked. Could have been done by any of the ways that we've looked at already. How can we now minimize the impact of that to the user? Well, let's walk through the logic of this for a moment. So first of all, because someone has suffered from a session hijacking risk, it doesn't mean their credentials are exposed. It just means that session ID has been exposed. The attacker has enough to now effectively go and impersonate the user. Now, because of that, if we can actually drop in an authentication challenge at some point in the workflow of the application, the attacker's not going to be able to meet that challenge. They're not going to have valid credentials. Now, of course, you don't want to do this on every single resource, or it would be a usability nightmare. But as an example, let's imagine it's a banking application, and before you can transfer more than, say, $10,000, you need to provide your credentials again. That's not too much of a usability barrier for most people, and it mitigates that session hijacking risk, because even though an attacker may have someone's session, they can only transfer up to $10,000. So that is a good mitigation. The other thing it does protect against as well is this age-old attack of someone simply sitting down at the victim's PC. Now, of course, whether they're hijacking a session remotely or sitting at the PC, it is usually the same end result. But these are two really good examples of scenarios where simply asking for credentials again at the right time in the process of the app does reduce the impact of an otherwise successful session hijacking attack. The first tool I want to look at in this module is the OWASP Z-Attack Proxy, or as we commonly know it, ZAP. Now, ZAP is great for a couple of reasons. The first reason is it's free. You can jump on over to OWASP and download it now without having to pay a cent. So that makes the barrier to entry very low. But it is also an enormously powerful tool, and it's particularly good at proxying the traffic from your browser and then enabling you to manipulate that traffic such that you can see how the application behaves under different circumstances. And that's exactly what we're going to do now. So let me jump over to ZAP, and it is currently running. Now, the thing about ZAP is we can use it to proxy all our traffic through, and as soon as you open it up, it's ready to run. Now, what I want to do is set ZAP so that it breaks on all requests and responses. So I'm going to turn this on. Now, what that means is the first time a request actually goes through the ZAP proxy, it's going to pause and let me inspect it before it proceeds. So let's now jump over to Chrome and get it to proxy its traffic through ZAP. Okay, we're in Chrome. Let's jump over to the settings, and I'm going to look for proxy, change proxy settings. I'm going to go over to my LAN settings, and I'm going to make sure that I turn on the proxy server. Now the address is just the local address, 127.0.0.1, and the port is 8080. Incidentally, the same port that Fiddler uses, so don't run both of these at the same time. So we're now going to say OK to that, and then close our settings and simply reload the page. Now as soon as I do that, I'm automatically flicked back over to Zap. And in fact, what we're looking at here is the GET request that we just made to local.hackyourselffirst.troyhunt.com. So Zap has indeed added a breakpoint on the request. So the request actually hasn't gone through to the server yet. It's been stopped at the proxy. And if we snap this to the right for a sec, we can see that Chrome is still actually trying to load. So clearly it hasn't actually received a response yet because Zap has stopped it. It hasn't actually allowed it to go through. So let me just maximize Zap again, and we'll have a look at what we've got here in this request. So I'll give us a little bit more room just here. And one of the things you'll notice down the bottom of this section is we've got the session ID. And we can see that we have one of these terrible sequential looking session IDs again. And one of the things that we can now do with Zap is actually manipulate this session ID before it gets sent through to the server. So this is a great way of saying, hey, how does the application respond if I try and change the session ID to what I think might be someone else's? So let's do that. Let's change that last 4 to a 5. And now that I've done that, I'm going to go up and turn off the breakpoint. And then I'm going to go over and allow that request to go through. So it's going to submit it and then just continue to step through the remaining requests. So you can see them all just appear there suddenly. The first one is obviously the request for the home page, and then we're seeing all the other assets loaded. So let's now flick back over to the browser. And here is something interesting. So take a look at the menu bar. We're no longer seeing login. We're seeing hello Mark. So what I've done is I've just changed that session ID to the session ID of someone else. So effectively, I have demonstrated that I'm able to hijack another session just by manipulating the session ID to a known value. Now this hasn't actually changed my cookie. And in fact, if I hit F5 to refresh the browser, we'll see it now says login again. So this time Zap didn't actually intercept the request and break on it. It just passed right through the proxy. So Zap is a great way of intercepting requests, taking a look at how they're constructed, and then manipulating them in order to test weaknesses in things like session IDs. Now that's only a very, very small part of what Zap does. It is much more powerful than just changing attributes of the request, or the response for that matter, but it is one good example of how you can make testing for the risk of session hijacking just that little bit easier. So that's Zap. Let's now move on and take a look at Burp Suite, and I'm really interested in looking at the strength of those session IDs. Burp Suite is an exceptionally powerful security analysis tool. It has a whole raft of different features for testing all sorts of aspects of web applications. Now, like Zap, it can act as a proxy. So we're actually going to pass some traffic through Burp and then use that to run some further tests. In fact, what we're going to use is we're going to use the sequencer tool. And as you can see here, it's for testing the randomness of session tokens. So we're going to use the free version of Burp, and there is also a commercial version, but we're just going to focus on the free one for the moment. We're going to use it to figure out how strong the session tokens in our vulnerable app are. And then after that, I'm also going to use it to demonstrate what a strong session token should look like when we run it through the sequencer tool. So let's jump over to the Burp app now. So this is Burp Suite. And as you can see by the title bar, it is the free edition. Now Burp Suite has a whole raft of different functions that you can use to test the security profile of your app. We're going to use the sequencer today. And the first thing I need to do before using the sequencer is actually capture a request which we can then use to test the strength of our session tokens. So Burp Suite is open. I'm going to jump back to Chrome. We're still here on the same test site. I also still have Chrome proxying through the same IP address and the same port. Burp also uses port 8080 on the local host. So it's just like Zap and Fiddler in that regard. And again, do make sure that you're not running multiple proxies or listening on the same port at the same time. I've closed Zap, it's just Burp that's running now. The app is presently configured to persist the session ID by cookie. And what I want Burp to capture is the process that sets the cookie. Now, as soon as you start a new session on this site, you get a cookie. So what I want to do is emulate that, which means I'm going to jump into the DevTools with F12, go down to my cookies, into the cookies for this website, and I'm just going to delete out the session ID. Now I'm going to give the page a refresh. And now you can see us jump straight into Burp, because just like Zap, as soon as it actually gets a request that goes through the proxy once we start it running, it's going to jump to the forefront of the screen. We can see the proxy tab is orange, so there's something new there. Let's jump in and take a look at that. And here we can see the request that we just made. local.hackyourselffirst.troyhunt.com. We're seeing port 80 because it's just running on the default HTTP port. And then we see all the request headers below it. Now you'll notice we don't have a cookie for the session ID. We deleted that before we reloaded that page. And this is the key thing. This request would normally respond by actually setting a session ID because it doesn't have one already. But we've captured this request early, before the site has had a chance to respond. And what I'm going to do now is just jump over to Action and send to Sequencer. Now, as soon as I do this, you'll see the Sequencer tab goes orange. So there's something new there now. Let's jump over there, and we can now see this request in the Select Live Capture Request section. It's the only one there, it's highlighted. And then just below that, in the token location within response, we can see that cookie is already selected, and it's selected the Visit Start cookie. Now I'm going to drop this down because that's not actually the cookie I'm interested in. I'm interested in the Session ID cookie. So let's select that, and now I'm going to go over to Start Live Capture. Now, as soon as we do this, we can see that next to live capture, we've got the tokens ticking over. The number is incrementing next to tokens. A little bit further over to the right, we can see the requests incrementing. And what's actually happening here is Burp is making requests to the website identical to the one that I sent to the sequencer. And on each request, it's going to be getting a response that has a new session ID. So every one of these requests is effectively starting up a new session on the server. And because of that, it's getting this new ID. And what Burp is now going to do is give us the ability to actually analyze those session IDs and see how random they are. Because remember, this was one of the big problems we spoke about early on. Session IDs need to be random. They can't be predictable. And this is the whole point of what we're doing here, to test how random the session IDs are. Now this has already captured a bunch of session IDs. I'm going to go up here and click on Analyze Now. We can let it keep running as well. We don't need to stop it right now. And here we see quite an important observation. The overall quality of randomness within the sample is estimated to be very poor. Now we know they're very poor because they're just sequential IDs. And in fact, what it's telling us just below that is that the estimated entropy of these IDs is 0 bits. This is clearly a very, very bad result. Now there's a whole bunch of information we can get about the strength of these IDs. We don't quite have enough results to do a character level analysis, but I'm going to show you that in a moment against a strong ID, but we can look at the bit level analysis. And I'm showing you this merely to indicate just how extensive Burp's analysis of the session ID strength is. So I'm just going to maximize this for a moment so we can see a bit more. And we've got a bit of a graphical analysis of just how terrible these session IDs are. We've got all sorts of different options we can run through here. And they're all basically different ways of telling us just how bad our session IDs are. We can also copy those tokens onto the clipboard or save them somewhere else locally just in order to check and see for ourselves what we know already just to be a sequential number. But the real point here is that Burp has been able to analyze them for us and give us back this information. Now it's pretty obvious when a session token is just sequential, but very often session tokens are still weak, even though it may not be as obvious as just an incrementing number. So running session tokens through the Burp sequencer is a really good way of getting an accurate, independent and objective piece of feedback about how good your tokens really are. Now this begs the question, what does a good token actually look like? Well, earlier on I talked about ASP.NET's session ID. And in fact I showed you how the live website was using the default session ID implementation, which is actually very good. So I'm going to go and point Burp at the live site. I'm going to just repeat this process. So let me go and do that, and then we'll jump back over here once I've got a good set of results, and we'll see how these results differ for a good session ID. Okay, that's probably about enough requests now. Let's go and pause Burp so we'll stop it issuing HTTP requests and getting new tokens, and we can review the analysis that's already here. I checked the Auto Analyze checkbox, which causes Burp to run the analysis on a pretty regular cadence as those session tokens are being received. And we can see a very different result here. So first of all, the overall quality of randomness is excellent. 113 bits of entropy according to Burp. We'll maximize this window again as well, and you can get a bit of a sense just by scrolling through the page as to how detailed Burp has been. We've now got enough data for character level analysis as well, and Burp will actually go through and look at each of the characters that appears in that session ID and assess just how random each one is. We can break this down and look at things like effective entropy, the character count analysis, character transition analysis, character sets, and then of course all that bit level analysis that we saw from earlier on with our bad session IDs, but this time with a very well formed session ID. There is a lot of information here, and it's all just about how strong those session IDs are. Now Burp does a lot more than this. It's great for capturing and modifying requests and then replaying them to test for vulnerabilities. In fact, in my ethical hacking SQL injection course, I also use Burp to do some fuzz testing. So in that case, I use it to automate the process of actually testing for potential vulnerabilities related to SQL injection. So it is a very powerful tool, but I thought this was a good example of one specific thing it does that's very effective when you're looking for the risk of session hijacking. So that's Burp Suite. Let's move on now and have a look at dynamic analysis testing with NetSparker. I really like NetSparker as a tool because of its simplicity and its breadth. And you'll see what I mean by that in just a moment when we actually run a scan. Now NetSparker is a commercial product. You do pay for the privilege of all this automation and ease of use. There is a free version available as well, but the functionality is somewhat limited. So what we're going to do now is just look at a brief demonstration of that commercial version and dig in a little bit to some of the things it can find that can be very helpful when looking at the risk of session hijacking. So here's what we see when we first open up NetSparker. I've dropped in the URL of the site I want to test up there in the target website /service URL. And NetSparker can be just as simple as clicking on Start Scan. And that's it. Now NetSparker is dynamic analysis. So what that means is it's going to run against a live running website. So a little bit like we just ran Burp when we were using the sequencer to test the session IDs that were generated. What you're seeing now is NetSparker going out and crawling the website. So it's finding all the different resources on the website, all the links, all the form actions, what are the possible behaviors of the site, and then it's probing each one of those for vulnerabilities. And you'll start to see issues appear here. issues of all different types of security nature. NetSparker does take quite a while to run, even on a little website like this. So I'm going to let it keep going, and then we'll jump back to here once it's finished. So here we are. NetSparker has now completed, and it has found rather a large number of things. 186 issues, apparently. I want to point out just a few ones as they relate to session hijacking. So for example, we can see that there is a cross-site scripting vulnerability, and in fact that is occurring on the search page. Now this is precisely the resource that we used when I hijacked the session ID cookie. So this was the one where it embedded an image in the page, and the source of the image was on the attacker's website, but it also passed the cookies over in the request. And that's this URL here. We can see the NetSparker string here, which has been used to test whether that untrusted data was reflected to the output, which clearly it was. And this would be a very important finding. In fact, NetSparker has actually flagged it right there as important. We know now what cross-site scripting can be used to do when it comes to session hijacking. We can also see another finding down here that puts us at risk of session hijacking. Cookie not marked as HTTP only. Let's have a look in there. And here we can see the identified cookie is session ID. We are setting a cookie called session ID and it is not HTTP only. Now this is a confirmed risk. It's very easy for an automated tool like NetSparker to see that yes, indeed, there is a cookie that doesn't have an HTTP only flag on it. It has classified it as low though. And of course you need another risk, such as a cross-site scripting risk, in order to take advantage of an HTTP only cookie. But again, this is all information that can be used in a session hijacking attack. And it's just been found automatically and represented here in a nice GUI with very easy to read information. And this is why I like NetSparker as an automated tool, because it is point and shoot, and it does make the discovery of these sort of risks extremely simple. You know how to find these yourself now, things like cookies not marked as HTTP only. But I'd far prefer a tool to go through and do that in minutes, as opposed to the humans sitting there for some long period of time trying to discover this themselves. The other thing, of course, that you know by now as well, is how to actually exploit this risk. So using a tool like NetSparker to find the risk in the first place, and coupling that with your knowledge of how to demonstrate what can go wrong when the risk actually exists, is a really powerful combination. So that's NetSparker. Let's move on and just take a brief look at a few other tools before we wrap up the module and the course. I want to talk about a few other tools and touch on them in particular for those of you who are interested in achieving your CEH, because these are tools that you'll often see referenced when it comes to session hijacking at the TCP level. So for example, Juggernaut. And as it says here, Juggernaut is basically a network sniffer that can also be used to hijack TCP sessions. Now, I'm showing you this not because I think it's relevant to now go out and use Juggernaut to look for risks at the TCP stack, but to point out that, as I did when we actually went through the network level hijacking module, that some things here are a little old. And you can get a good sense of that by looking at the comments here. The newest one is 5 years old at the time of recording. The other comments are 8 and 9 years old. This is a very old tool, yet you'll still often see it referred to as a means of automatic testing for session hijacking risks. So as I said in that module around the network level, to some degree treat this as a bit of a history lesson. Let's go and take a look at another one. The Hunt TCP hijacking tool. No relationship to my namesake, but it is a tool which is frequently referenced in the same context as Juggernaut. But again, I just want to give a bit of context of the generation of this tool. And if we go and have a look at the home page of the tool, we'll get a pretty good idea of how well maintained this is. So yeah, that no longer exists. If we go back to the site again, and we scroll down, and we also take a look at the comments of this one, the last comment there, in fact the only comment there, was from 10 years ago. Now, there is a note here about where you can actually go and download the Hunt tool from via Packet Storm Security. So we'll take a look at that. And the last version here was from more than 15 years ago. Now again, I thought it was relevant to show you this just to put into context how relevant some of these tools still are today. A tool that hasn't been maintained for a decade and a half really doesn't have a lot of modern day relevancy. But again, you will see it referenced in a lot of material, so I did want to touch on it here. But as the risk of network level TCP session hijacking has waned over the years, so has the relevancy of these tools. There is, however, one other tool which does still have some life in it. Let me show you that one quickly. This is Ettercap, and as you can see here, it supports active and passive dissection of many protocols and includes many features for network and host analysis. This is an automated tool that can be used for network level session hijacking. And unlike Juggernaut and Hunt, it does still have some life left in it. In fact, if we go and take a look at the GitHub repository, the last commit was only 15 days ago. So clearly it has a lot more relevance than the projects that were last updated 15 years ago. So if you did want to pursue network level session hijacking, Ettercap would probably be a much better place to start than some of the other alternatives which you'll see referenced in network level session hijacking material. So that's just a few examples that hopefully give you some context of just how relevant or irrelevant as it may be some tools remain today, but also to show you one that could actually be quite useful if you did want to pursue the more obscure corner of session hijacking, that is TCP level hijacking.